Today, we're going to move over to an entirely new type of algorithm. And this algorithm is often computer scientists' favorite algorithm because you're going to find the results of hashing is going to give us a fantastic runtime for certain operations. Let's dive into what it means to do hashing. Mathematically, we define hashing as a key space that we want to transform into a number of different values. So everything inside of our key space is going to be every possible key that we can have inside of our dictionary. And our goal of a hash table is to be able to map every single key to the value that it contains in that dictionary, and do so as quickly and as efficiently as possible. You may already be familiar with hashing if you've ever used a dictionary structure in a language like Python or JavaScript. At the core of these native data types, we have the idea of hashing. Let's go ahead and look at what it might mean to actually do some hashing. So for example, let's look at a hash table. And the first example I can remember about hashing is thinking all the way back to high school. In high school, I went to a large school that had a number of lockers, and every single person was assigned a locker. And I remember all the way back from my high school days that here in this hash table, I was assigned the locker 103. So that was my locker. And then I knew the locker numbers of some of my friends because they were if I wanted to see some of my friends between courses, I would go to their locker and meet them at their locker. And that way, I could find exactly where they were going to be located. I could go directly there. Even to this day, I remember some people's locker. One of my best friends, Blake, was at locker number 92. And there's a number of different lockers here at the school. The one thing to note is that the lockers are a unique key value, that every single locker has some integer number, and that locker is associated with some data. The data here is the name of the person who owns the locker. I imagine somewhere in the administration, there was a mapping between the student who owned the locker and the locker number, so that given any locker number, you could quickly look up which student had that locker. A hash table is going to allow us to do exactly that. We're going to input a number into our hash table, and we're going to use some function so we can go ahead and map every possible number input into a fixed-sized output. Because ultimately, in a locker key space, we might know exactly how many lockers there are, but we may also consider things like an identifier, such as a social security number or other identifier. That may be a random number that's not entirely filled up in the key space. So we know the key space can be any possible integer, and we want to be able to map any possible integer into our output space. So the entire goal of hashing is always going to revolve around this diagram. Here we have input coming in. This is going to be something like an integer. Some function that we're going to define later that's going to transform this function, this integer, or a string, or whatever our input is, into a number that is in the range 0 to whatever the size of our array is, which I'm going to call n. The transformation of this key input into a number, and then how we manage that array, and ensuring to deal things with collisions, is exactly what we're going to be talking about as we talk about hashing. So specifically, when we define a hash table, there's always going to be three things at play, and we're going to dive into what each of these three things means. The first thing is we need some function, a hash function, that's going to map our input space into an array index. So if we have a string as our input, we need to map that string from the string input type down to some integer between 0 and n. The second thing we need to look at is we need to actually have an array that stores the actual data. So notice that here at the hash table, we have an array that's going to store our data that's going to be indexed in by our hash function. The very last thing is we can imagine that sometimes we're going to have two things at the same spot in the array, and we know that's not allowed. So we need some way to decide what we want to do in collisions. So when we have collisions, we want some collision handling strategy that's going to allow us to handle the collisions that occur when our hash function maps two different values to the same point on the array. The combination of all three of these ideas is going to be the subject of this week's videos, and we're going to dive in to exactly what it means to build a good hash function, what it means to have a good strategy with our array, and exactly what we do when we do have collisions. So while this may be a little confusing right now, it'll become clear as we move through these videos. Let's get started with the hash function in our next video. I'll see you there. To really understand what a hash function does, let's take a look at a couple different hash functions through examples of data being put into a hash table. So this first example is a number of faculty who teach courses here at the University of Illinois. Here at the University of Illinois, there are courses like 241, which is taught by Professor Lawrence Ongrave, 421, Professor Beckman, 210, Professor Cunningham, 101, Professor Davis, Carl Evans teaches 126, Professor Fagan-Olmschneider, teach 225, and we can see that the list goes on and on and on. Here we need to figure out a function that allows us to map all of these names into an array index. So if you noticed, I chose a particularly unique set of professors and listed them in a particular special order so that we can have a really great function. Notice that there is exactly one professor for every single name in the alphabet. Our key function here may be the function where we look at our key string and we take index 0 and we subtract the character value a. So Ongrave is going to be character value a minus character value a, which equals 0. So our key Ongrave is going to be placed in index 0, and his value is 241. Beckman, b minus a, is going to be equal 1, and Beckman can be placed into the second index, or the second position, index 1 in our array, for 421. And we can continue this on, and you'll notice that C goes into index 2, D, E, F, G, and H. Each of these letters have a perfect mapping into our array from our key space. And in fact, every single element in our array is filled and has a unique mapping back to the original data. This idealized hash function, this perfect hash function, is something we mathematically call an onto function. That every single element in the array is full, and we can map every single element into our data onto that array. This is an amazing setup, and that's going to be the absolute goal of what we want. But there's a slight problem. A new faculty might have arrived who had a name that's similar to one of these names. When we have to consider that faculty member, there's no longer space. So if we have a new faculty member, Professor Charles is unfortunately going to land right here where Professor Cunningham is currently at. That's a problem, and we're going to need to handle that collision. So let's remember that problem, and we'll deal with it again in a second. A second hash function is one of my favorite dice games. So whenever I have a group of people, and if you were here in person, I would roll a number of dice for you, and I would show the result of this dice and give you a number of what that dice is. So here, let's look at this set of dice. Here we have a dice that has the pips 1 up, 2, 3, 4, and 1. I would give you the number 2 as the mapping to this set of dice. I could roll this dice a number of times and give you a different set of numbers. And what I'm doing is something called petals around the rose. This is a particularly fun example because it will take a while for people to figure out, so I encourage you to try it. But what I'm doing is I'm simply counting any dice that has a center pip that's active, such as the 3, and counting how many petals are around that pip. Here 1, it does have the center node, but has no petals around it. 4 doesn't have the center node, so I'm not counting it. Only 3 and the dice 5 are counted in petals around the rose. So here my hash function is the function petals around the rose. This function allows us to look at any set of input, here our input are dices, and map that to a value inside our array. So looking at this first set, where I have the dice 1, 2, 3, 4, and 1, my hash function, as we discussed earlier, maps it to 2. So that means here in 2, I have the value 1, dice 2, dice 3, dice 4, and dice 1 again. So we know that the value 2 is going to map to that data or some other information associated with it. One thing I might do is actually just keep a tally of exactly how many there are. So let's actually discuss some things that are going to happen to this hash table. So given that we know that there's always going to be either 2 or 4 petals around the rose, think about what happens for the hash value 1. Will anything ever get mapped to 1? It won't. The only way we're going to count petals is for a 3 we count 2, or for a 5 we count 4. So every single odd number is never going to be reached in our hash table. So this hash table is not going to be perfectly filled. And if we think about all the possible rolls of a dice, think about the fact that we may have a lot of rolls that contain just a single 5. So there may be a lot of different values that get mapped to the value 4. Both of these problems are concerns that we need to have to ensure that we have a great hash function. We need to consider a hash function that works really, really well for all of our key spaces. And there's going to be 3 characteristics that we can analyze to determine whether or not we have a great hash function. So to dive into this hash function, we want to look at the hash function in 2 different pieces. The first piece of the hash function that we need to look at is we need to look at the function itself, how we transform whatever our input is into a number. So we say the hash itself is going to transform an input into an integer. Here in this initial transformation, I'm often going to not worry about the bounds of that integer. So I just need some generic function that's going to turn whatever my input is into a numeric form, into an integer form. The second part of my hash function is going to be a compression to make sure the hash function is within the bounds of the array. The compression can be easily done with a mod operator. So I can do that using mod in. So I encourage you, as you're thinking about hash functions, to not create a new hash function yourself yet. That is actually really, really hard to make a good hash function, and there's some amazing hash functions out there. So we want to understand how to analyze a hash function before we go about creating our own. As I mentioned earlier, there are 3 different characteristics that we're going to care about when we're building a hash function. The first one is we need to make sure our hash function runs in constant time. We want to ensure that the time to compute a hash is going to be O of 1. We need to absolutely make sure our hash function runs in constant time, and we would prefer if this was a very, very, very fast function. It is absolutely essential that the computation time of the hash is extremely quick. If we're spending a long time computing the hash, then we're going to spend a long time in this algorithm because we have to compute the hash every time we see a piece of data. So the first thing that makes a great hash function is the hash function must run in O of 1 time. The second thing we need to absolutely make sure is true about a hash function is the hash function must be deterministic. What this means is if we hash a string once and we hash the exact same string a second time, those 2 results must be exactly the same. What we cannot do is throw a random number in there. We might love to do this because it'll randomize exactly where our input is in the result. But by throwing a random number in there, we no longer have a deterministic hash. Every time you want to hash the number 103 or hash the string Wade, you absolutely must ensure that that string comes out at the other side as the same index into our array. So the hash function's second requirement is it must be deterministic. The third requirement is the hardest requirement to ensure is true. And this requirement is called the simple uniform hashing assumption, or SUHA. The simple uniform hashing assumption says that the result of our hash algorithm must be uniform across the entire key space. So what that means is under SUHA, it means that given 2 values, so we're going to take the hash of some value a and a second hash function of b. When we hash these 2 functions, we need the probability of the hash of a to be equal to the hash of b to be equal to 1 over the size of the array if a does not equal b. So if we have 2 different values, the simple uniform hashing assumption says that at random, 2 values are going to randomly be in different places in the array with equal probability. Anytime you have bunching of data, such as the petals around the rose example earlier, where you have multiple pieces of data hashing to the same value, and some of that data never hashing to odd numbers, we no longer have a simple uniform hashing assumption. Because you can see the probability of hashing to 1 is 0, while the probability of hashing to values like 2 or 4 was quite high. So if we have a function that runs in constant time, is deterministic, and is a simple and satisfies the simple uniform hashing assumption, then we have an absolutely great start to building a great hash function. We'll largely use other people's hash functions for most of our work here since it's so hard to ensure that uniform distribution, but we'll do some analysis on hashing functions to understand exactly their runtime. We'll talk about some of this analysis and dive into a few more examples in the next lecture. I'll see you then. So as we talk about building hash functions, it may seem initially to be very, very easy to build a hash function. We can think about all of the data that we might consider as part of our hash function. We can think of a pretty easy mapping to it. And in fact, for small values of input, this is going to be extremely easy. I can think about what my data is. I can think about what I expect my user to input. And I can map it in a relatively uniform way. And it's not going to be hard. But what often happens is when you actually see a code move into production and not simply be something you're thinking about in your office, you're going to find that the actual amount of key space is going to be much larger than you imagine. And we need to have a hash function that considers all of this key space and not just what the user expects. So here, instead of just mapping to a small key space, we have to consider the fact that our circle may be here or maybe way out here. And in doing so, we have different parts of the key space we need to consider, and all of these subspaces of the key space needs to be uniform. This is incredibly difficult to do. So one of my examples that I ran into when I personally tried to create a new hash function was that I wanted to map strings that were of some arbitrary length, and I went ahead and I created a hash function that mapped a string of arbitrary length by mapping a string of only 8 characters. And I figured, you know what? A string of 8 characters is really easy to create a hash function around. I'll sum up their values, do some mod and some multiplication on them, and I will have a really great system to make sure that every string is uniformly different. So here I have the text of Alice in Wonderland. This text has a lot of different sentences, and if I look at the first 8 characters of every single line, I can see the first 8 characters of every single line is quite different. There's no 2 lines that are the same. And if I look at the first 8 characters and do some clever math on them, I can come up with numbers that are going to be different at every single point of time. I think I am really confident in my ability to actually create a hash function that's going to map each line of Alice in Wonderland to a particularly unique value, or at least in a uniform way. Awesome. So created this hash function. It did a great job. It worked great on some text corpuses. But then as soon as I went and plugged this into a different application I was building, some weird things happened. So the next thing I built was a web scraper. And I was scraping Wikipedia articles to do some research on the text in the Wikipedia articles. In doing that, the keys to my hash table, the data point that describes what data I have, the key value, was a URL. So using the exact same hash function, I looked at every single URL. And let's look at the first 8 characters of those URLs. In Wikipedia, the first 8 characters of all the URLs are exactly the same value. So here, every single point in this data set has a number of values that are mapping to the exact same point. What that means is every single point I have a collision, and I have a number of different collisions happening. And I have to resolve all of these collisions, and I absolutely do not have a uniform set of functions. Because of this, I actually developed a hash function that worked really, really well in one piece of data. And then as soon as I used it in another application, I found this hash function fell apart. So these are some of the problems that we're going to deal with when we deal with hash functions. It's incredibly hard to think of all of the uses the user is going to use. So whenever we think about a hash function, we want to be very, very careful. And if at all possible, we're going to use some of the established hash functions that have already existed for many years, because the best way to test whether or not a hash function is good is to use it for a really long time. So we've talked a lot about the hash function, and now we're going to talk more about diving into the next aspect of this, about the array and how we deal with collisions. So I'll see you then. Up until now, we've talked a lot about hashing functions. The hashing function is going to sometimes result in a collision where 2 different inputs are hashed to the exact same value. Under Suha, this should be rare. but it may happen quite often if we don't have a strong hash algorithm. Let's look at some strategies to deal with this. The first strategy, the idea of separate chaining, is going to be a strategy where we're going to dive into the array, but treat it more like a linked list. Every time we run into a collision, we'll simply add the element to the linked list. Let's look at how this might work. Here I have a number of values in my set S that I'm going to be inputting into our hash table. Our hash function is kmod7. So here we're going to take the value 16, mod it by 7, and we get a remainder of 2. So we know we need to hash an index 2 and add the value 16 to value 2. Here our array, instead of just being an array of values, it's an array of linked lists, where each list is initially empty. Next value, 8. 8 mod 7 is 1, so we go ahead and add 8 to index 1. Next value is 4. 4 mod 7 is 4. And go ahead and add that right here. Next value is 13. 13 mod 7 is 6, so we can add 13 off of 6. Now we have 29. 29 mod 7 is 28 remainder 1. So here we have a value of 1. Now we have a collision. When we have a collision in separate chaining, we can simply look at this and say, how can we insert into a linked list as quickly as possible? And from earlier in the semester, you learned that inserting into a linked list can be done in O of 1 time if I insert at the beginning. So in separate chaining, whenever we have a collision, we're just going to simply insert at the beginning of the linked list. Let's do that here. Here we're going to go ahead and move 8 out of the way to put 29 at the front and then link to 8 afterwards. Next element is 11. 11 mod 7 is 4. We have another collision, so we put 11 at the front, moving 4 back. And finally, 22 mod 7 is another collision, and it maps to the value 1. So here at the front of 1, we have 22. That then points to 29 and then points to 8. So using separate chaining, we have an ability to deal with collisions by simply adding to the linked list. You can imagine the very, very worst case of this algorithm would be quite bad. If we had a hash function that always kept returning the same value, what we have is we have a linked list that grows in size equal to exactly the value of the number of data in our hash table. That means our algorithm is going to run in O of n time if we ever have to find something inside that hash table. This is going to be really, really bad. And down here on the right-hand side, we see the worst case for an insert is O of 1, but the worst case to find it is O of n. If we have the simple uniform hashing assumption to be true, we know that the insert time is still O of 1. We can always insert at the front of the linked list. But the remove find, we're going to express in a new variable, a variable that I'm going to call alpha. This alpha is going to be the load factor of the table. So load factor of the table is alpha is going to be defined as the number of elements inside of the table divided by the size of the table itself. So little n divided by big N. This term determines how full the table is. A load factor of 1.0 means that you have exactly as much data in the table as there is space in the array. A load factor of 0.5 means on average the array is half full, or we have linked lists that would fill up half the array, or half the table if we put them in there. A load factor of 2 means that on average every single node has 2 items in the linked list. So you can see as the load factor grows, the amount of time it takes to run this algorithm is also going to grow. Here we have just one strategy of doing separate chaining. And in the next video, I'm going to discuss another strategy that's going to take a completely different approach to doing this. I'll see you then. A second way to deal with collisions inside of an array is to use something called probe-based hashing. This collision strategy doesn't use a list whatsoever. Instead, we're going to develop an entirely new strategy to deal with this. To do that, we're going to consider an array just like before, but now our array is actually going to store the data, as opposed to being a linked list. And let's take a similar input set and run it through a similar hash function, and use a different strategy when we run into a collision. Here we have this same set of data and our same hash function. I'm going to go ahead and run through this just as before. 16 mod 7 is going to be 2, so I'm going to add 16 to index 2. 8 mod 7 is going to be 1, so I'm going to add the value 8 to the index 1. 4 mod 7 is 4. I'm going to add 4 to index 4. And then 13 mod 7 is going to be 6. I'm going to add 13 to index 6. Now we're at 29. 29 mod 7 is 1. And now we go to our new strategy. In probe-based hashing, if we run into a collision, instead of simply using a linked list to handle a collision, we're going to simply look at the next location inside of the array. By looking at the next location, we're just going to probe ahead until we find an empty slot. Once we find that empty slot, we can write the value right there. So looking at this example, here at 1, we can't enter 29 at 1 because we already have 8 there. So we need to probe ahead. 16 is also filled up. So probing ahead again, we can finally put 29 in index 3. Next to 11. 11 mod 7 is 4. We look at index 4. We find index 4 is already filled up. We probe ahead and find that we can put 11 in index 5. Finally, we find the number 22. 22 mod 7 is 1. We have to start at 1 and now probe ahead until we find an empty slot. Notice that we have to go through the entire array, loop all the way around until we get to 0 before we can insert the value 22. We had to look at every single element in the array, and only our very last chance were we able to insert that data. You can imagine this is going to cause some problems. We may not want to just always insert our data at the same location, and we're going to find the runtime of this is going to be problematic. So we can express this mathematically by saying this simple function right here that we're going to try to do a single step every single time. But what's going to happen with linear probing when we probe one element at a time is we have something called a primary cluster that's forming. You already saw an intuition of this when we went through the example earlier. The intuition here is that as soon as you start getting a pack of numbers filling up, we're going to see that a lot of things are going to have to be probed until the end of the pack. So if you imagine this array, we have a number of elements that have been filling up right here in this space. It's getting pretty crowded. Lots of things are hashing here. We may hash another value here. So now if we hash to anything in this point, it's always going to be probed until this point right here. So we have something called a primary cluster. The idea that even with a uniform distribution, that based on the laws of probability, we're going to end up with a cluster that has a primary set of values all in a single block, while the rest of the array is going to be fairly sparse. The remedy to this is we want to make sure our probing isn't exactly linear. So let's do something called double hashing to fix this problem. In double hashing, instead of just having a linear probe every single time, we're going to have a secondary hash function that's going to allow us to hash into a new index that's not necessarily immediately following the other point. So let's look at it. Here, we can see that instead of saying k plus 0 times our current number of hashing, this was 0, 1, 2, we're going to multiply 0 by a new hash function. So here, given a key and given the number of times we're hashing it, we have h1 is going to be our first hash function. This is k mod 7. Well, h2 will be our second hash function by how far we need to jump at each point. So in our second hash function, we want this to be an output of some value that's going to be not 0 and less than the size of the array. So one can imagine that our second hash function might be something like our mod value 5 minus our key mod 5. So here we know that k mod 5 has the output range of 0, 1, 2, 3, or 4. So 5 minus 4 is 1, 5 minus 0 is 5. So our step function is either going to be 1, 2, 3, or 4, or 5 when we do double hashing. Diving into this example to really see what's going on, we're going to start with 16. 16 mod 7 is still going to be 2. So we go ahead and enter 16. 8 mod 7 is 1. We enter 8 at index 1. 13 mod 7 is 6. We insert 13 at index 6. And I skipped 4, but 4 is totally fine to do it now. 4 mod 7 is 4. And we stick 4 right here at index 4. Now we get to the point where collisions begin. 29 mod 7 is 1. And now we have a collision at 1. So because we don't want to simply do linear probing, now we need to apply double hashing. That means we're going to apply a second hash function. let's go ahead and do the second hash function. 29 mod 5 is going to be 4. 5 minus 4 is 1. So we're going to do linear probing on 29. Our step function's 1. That's fine. We only need to jump 2 spots. We can go ahead and put 29. Second number we get is 11. So 11, using our original hash function, 11 mod 7 is 4. 4 is filled up. But using double hashing, we now are going to use our second hash function. We have 11 mod 5, which is 1. 5 minus 1 is 4. So our step function is 4. So looking at index 4, we're going to jump ahead 1, 2, 3, 4 indices, and then jump 4 more ahead. 3, 4, and find that we go ahead and insert the number 11 right here, immediately following 4, but we did so using a different process. What we find is when we do this on a large scale, that this approach of randomizing how much we step at each time is going to avoid the idea of a primary cluster. Though the big idea you should take away from this is no matter what strategy we use, as our hash table becomes full, we're going to see our performance degrade. And we can actually quantify this by looking at the load factor and the amount of collisions that are required to resolve the collision to find an open spot as functions. I've done this for you, and we did a lot of math to get to this point to find out the exact equations using linear probing, double hashing, and separate chaining to find out the total number of collisions that are expected and the running time to insert using these different techniques. The goal of these equations is not to understand the equations themselves, but to understand how the equations behave as the load factor of our hash table changes. So what this means is we can look at these equations and see where is alpha in all of these equations. So here alpha is in a denominator. Alpha is in a denominator. So as alpha increases, you're going to see that the running time is going to be 1 minus alpha, 1 minus alpha, 1 minus alpha. So the running time is going to get worse the larger our load factor is. This intuitively makes sense, that as alpha increases, the running time of our hash table gets worse. And I don't have an intuition of exactly how these functions work, so I went ahead and graphed these functions so that we can actually see a graphical implementation of these functions. Using the graphical representation, I can see the load factor with linear probing shows that there's an absolutely small amount of running time as we go up alpha. So alpha here is on the x-axis. As we increase alpha, running time is here on the y-axis. As alpha increases, the running time increases as well. Likewise for double hashing, as alpha increases, it's flat for a while, and then the running time explodes as alpha gets close to 1.0. What this really shows is as long as we manage alpha, we can have a very predictable runtime of our algorithm. So specifically, let's look at having alpha be at the value of about 0.6. So if we manage alpha to always be at or below the value of 0.6, notice that the running time of this algorithm is extremely fast. These are absolutely amazing running times given an alpha value less than 0.6. What this means is it doesn't matter how much data is in our array. Our array can have 1 billion records, but because alpha is only the ratio between the actual amount of data in our array and the size of the array, as long as we can keep expanding our array, we can find that our running time is absolutely phenomenal, no matter how much data is inside of our data structure. Inside of our hash table, if we have 1 billion records or just 100 records, the running time is determined only upon the ratio of the amount of data in our hash table to the size of the array, and not the actual amount of data itself. So what this means is that the running time proportional to only the amount of data for any hashing technique, as long as we keep alpha constant, that running time is going to have an O of 1 running time proportional to the data. Because the running time is going to be proportional to alpha, not proportional to the amount of data in the array. The one last little bit to complete this whole idea is that we're going to have to resize the array every so often. So when we resize the array, we're going to have to be very, very careful about resizing this array. Because if we simply resize the array by copying every value over, as we've done with every other resize, you'll notice that resizing the array is going to change where values get hashed to, because we have a compression step that says whatever our hash value is, we're going to mod it by some value. The one important part to think about is to what happens when we do have to resize the array. Because the one thing we know is we absolutely need to maintain that ratio, that alpha value, between the number of data, the amount of data inside of our table, and the actual size of our array. As we learned earlier, when we resize an array, we're always going to want to double that array. And in doubling that array, we're going to have to do something called rehashing. So rehashing is the idea that if we take a value from the array, the original spot it hashed to is not necessarily going to be the new spot it hashes to due to the compression aspect inside of our hash function. So remember, our hash function gets in integers, then mods it by a value. If we consider this example right here, we might have originally hashed something to index 1. When we expand the array, that hash of index 1 may have been at 1, or it may have been at index 8 or 9, depending on the size of the array. Because of this, we need to make sure that when we expand the size of the array, we go through and rehash every single value in the array to make sure it's in the proper spot. Right now, we have a complete understanding of the entire hash table system. We know that we need a great hash function that spreads out our data uniformly across the table. We know that that function needs to be quick, deterministic, and satisfies SUHA. We know we have an array that we have to maintain the size of that array to keep a great ratio, an alpha value less than 0.6 to have extremely strong performance. And we know what we need to do when collisions do happen. That we have different strategies, either using a linked list or using linear probing or double hashing to handle these collisions. All of this gives us an amazing opportunity to develop a really awesome algorithm, do some really awesome things with hashing. In the next video, we'll discuss a final little bit of hashing and do some analysis on the entire system as a whole. So I'll see you then. So as we've talked about hashing, let's talk about some big picture items. One thing is we might want to determine what the better strategy to use is. Do we want to do separate chaining where we have a linked list of nodes? Or do we want to actually put the data inside the table itself? And we find that depending on the application you're using a hash table for, the right answer is different. If you have large pieces of data that are going to take a lot of time to copy inside the array itself, you absolutely do not want to use an array. You'd rather use a pointer, a linked list, to store that data somewhere else. So if we think about having big records, we're going to want to use something like separate chaining to handle big records. So using separate chaining for big records means that the other solution is probably better in some other way. And in fact, double hashing is great for structure speed. Remember that array operations are memory optimized because they're sequentially located in memory. So if we care only about raw structure speed, and we know our data itself is going to be fairly small, we can use a closed hashing technique such as linear probing or double hashing to actually run in a really efficient data structure. So for structure speed, we're going to want to do something like double hashing. So the structure, what structure does the hash table replace? Might be the next question we asked. That structure is going to be a dictionary. So an AVL tree also provides a dictionary implementation. And as we discussed with AVL trees, AVLs do a great job with range finding and nearest neighbor. A hash table does an absolute terrible job with that. You can't say what value is near 42 because 42 hashes to one particular spot in the array, and the values around 42 may have nothing to do with 42 inside of the actual final array, because 41 and 43 may hash to an entirely different spot in the array. So it's absolutely essential that we have the right algorithm for our right application. Because if we need to do nearest neighbor on a hash table, we're going to see ourselves running in O of n time. So which structure does a hash table replace? It replaces a dictionary. What constraints exist on a hash table that's not like a BST? As we just went over, the constraint that really exists is the idea that a binary search tree has a great nearest neighbor approach, while we have no ability to do nearest neighbor in a hash table. So when we think about what algorithm to use, we want to use a tree-like structure if we ever need range finding or nearest neighbor. We want to use a hash table if we're always going to have the exact key. If we're always doing lookups, hash tables are phenomenal. Hash tables are going to run O of 1 lookup times, and hash table and AVL trees are going to run log n lookup times. But when we want nearby neighbors, it's log n to do it in an AVL tree, order n to do it on a hash table. The very last bit is why do we talk about BSTs at all? And we talk about BSTs both as an introduction to the dictionary structure and because some of the most interesting problems that we're going to solve are not going to be solvable by a hash table. A hash table is a fantastic general purpose data structure, while an AVL is going to solve particularly great problems. If all you care is a lookup, the hash table is the algorithm for you. We're going to start using hash tables to build even more complex algorithms as we discuss more complex algorithms next week. So I hope you guys have enjoyed learning about hash tables. It's one of my personal favorite algorithms, and I'll see you next week for a number of new videos on an entirely new data structure. I'll see you then. In C++, a hash table is actually built in for us into the C++ standard template library. So we can use a hash table inside C++ with very minimal work. One thing that often people use for a dictionary is a map inside of a hash table. And a map has several operations that work really, really well. We have the index of operation, we have the insert operation, we have the erase operation. We also find that we have these lower bound and upper bound operations. And if you remember back, a map actually implements a dictionary, but it doesn't implement a hash table. A map, in fact, is an implementation of a red-black tree. So these operations are going to have a log-in running time. But instead, we have a different data structure inside C++ to implement our hash table. This data structure is called an unordered map. This unordered map is different than a tree in the sense that in a tree, we have the ability to do an upper bound and a lower bound search. We have that range finding ability. As we discussed previously, we have no range find ability inside a hash table. Instead, we still have the same basic operations. We can still find, insert, remove, and delete items from our hash table. But we have different functions because we have a hash table. The function we have in a hash table are getting things like the load factors. So inside C++, we can ask a hash table, how crazy big is it? Does it have a load factor of 0.5? Does it have a load factor of 0.6? And we can do something really interesting. We can set what load factor we want our algorithm to target. So we can target a load factor of something as terrible as like 1.0, when our algorithm's performance starts to degrade terribly. So if you want to be really mean to someone, you can ask the standard template library. We can have them really set up a really, really, really terrible load factor. All of this gives us the ability to program some C++ code using an unordered map to implement a hash table to give us these O1 guarantees as long as the load factor is correct. So now you never have to write a hash table. You can just use what's one in C++. I look forward to seeing some of your code as you work on using some hash tables. I'll see you later. This week, we're going to talk about something entirely different. Instead of talking about a data structure that seems really, really useful for common sets of data, we're going to talk about a data structure that's somewhat specialized, but it's going to have huge applications when we begin starting to talk about graphs. Specifically, we're going to talk about the idea of disjoint sets. A disjoint set is going to be a series of sets which are disjoint from one another, but every single element within a set is considered to be equivalent within that set. Let's take a look at an example to see what that means. So here are 4 disjoint sets. We have one set that contains the elements 2, 5, 9, another set that contains the element 7, another set with the elements 0, 1, 4, and 8, and a final set with the element 3 and 6. When we consider each of these sets, we consider every element inside of a set to be absolutely equivalent. If you're familiar with mathematics, this is something saying that these two elements are in an equivalence relationship with one another. As far as we're concerned, 2, 5, and 9 are completely indistinguishable. We can do operations on the disjoint set like the find operation. The find of 4 operation is going to find the set identity for the set that contains the element 4. So we can choose any single element to be the set identity or call it something completely different. Just to be really, really clear, I'm just going to always use the first element as my list to be the identity element for that set. So what this means is if we look at this set right here of 2, 5, and 9, the identity element for this set is 2. The identity element for this set here is 7. The identity element for the set 0, 1, 4, and 8 is 0. The identity element for the set 3 and 6 is 3. The big idea is we need to make sure that identity element for every single set is unique so that we can differentiate a set from one another, but we can now know that the identity of every single element within a given set is going to be the exact same thing. So when we find the element 4, what we're going to return is we're going to return the set identity for that element. So here, finding 4, we say the set identity of that element is 0. Likewise, one operation that we need to ensure is consistent is we need to ensure that find of 4 has the exact same value as find of 8. Because find of 4 and find of 8 both need to return the same set identity because both 4 and 8 are in the same set. In this example, we have 0 as a set identity, so both find of 4 and find of 8 are both going to return 0. 0 is equal to 0. So we see that by choosing a set identity, we can ensure when we do a find that we can find whether or not two elements are in the same set. The other operation that we're going to care about is not only do we need to find, but we may need to actually union two sets together. Once we add an element to a set, we can never separate it again. So by unioning two sets together, what we're doing is we are unioning the set that contains one element with the union of the set that contains another element. And the end result is a larger set that contains both elements. Look at an example. Here we're going to union the set that contains 2 and the set that contains 7. So the set that contains 2 is going to be this top left set, and the set that contains 7 is going to be the top right set. When we union the set that contains 2 and the set that contains 7, the new set is a single set that contains all of these elements. Now, 7 has a different set identity. Because 7 is in the same set as 2, 5, and 9, we know that the set identity for 7 now must be 2. Mathematically, we can talk about a set as being a collection of different sets. So a disjoint set is going to be a collection of sets where each set has a unique identity in it. As part of this set, we know that each set has a representative member, and that's going to be an element that uniquely identifies that set. And the only operations that we're going to need to program on this data structure is we need to go ahead and make a set out of a single element. We need to find the identity of a given element set. And the final thing is we need to be able to union two sets together. We're going to dive into how we create a really, really incredibly efficient algorithm to solve this particular problem all this week. So we'll start by looking at what we can do to build the structure in the very next lecture. I'll see you there. Let's think about how we might actually create an implementation of the disjoint sets algorithm. In doing so, I'm going to create the most simple algorithm that I can think of. And we'll look at how well this performs and what kind of problems that we have in this simple implementation so we can go ahead and build a more complex implementation that solves the exact same problem, motivated by the example we see right now. So what I'm going to do is I'm going to store all of the elements inside of my set into an array. So let's look at an example. Here I have the element 0, 1, 4, 2, 7, 3, 5, and 6. Luckily, this is the numbers between 0 and 7. And these are nice indices into an array. If we don't already have this nice index relationship, we can put a hash table in front of this using our hash algorithm that we learned about a few weeks ago to create an index that can be indexed into an array. So given these elements, I can simply say at every single index into my array, the value in the array is the set identity for that particular group. So 0 is in the group that has a set identity 0. The element 1 is in the group that has a set identity 0. The element 2 is in the group that has a set identity 2. The element 3 is over here in the group that has a set identity of 3. The element 4 is in the group that has a set identity of 0. The element 5 is in the group that has a set identity of 3. Element 6 also in the group with the set identity of 3. And finally, element 7 is the element which is in the set with the identity of 2. So notice the value in every single array is the exact identity of our structure itself. So that means to find the identity of a given element, so to find the identity of element 4, then we can simply look at index 4 in the array and find out what the set identity is for that. So looking at element 4, we know that the set identity for find of 4 is going to be 0. This is incredibly fast. We're just looking up into an array. We know that the running time of this is O of 1 time. This is an incredible running time for being able to find an array. But let's think about what happens when we need to union two things together. Suppose I want to union the element 4 and 2 together. Unioning 4 and 2 means that the entirety of the left set and the middle set must be unioned into one same set. What that means is 2 and 7 needs their set identities updated to be 0. Unfortunately, in our current implementation, we have no way to know what elements are in the element 2, or what elements are in the set identity that has the set identity of 2. So 2 and 7 are both in the same set, but no data structure here allows us to look up what all elements have the set identity to. Instead, the absolute only way to do this is to go through our array and say, hey, index 0, are you part of set identity 2? Nope. OK. Index 1, are you part of it? No. Index 2, you're part of it? Yes. OK, awesome. Then we need to update your identity to 0. Index 3, are you part of it? Nope. Index 4, are you part of it? No. Index 5, no. 6, no. Only here when we get 7, we find another element that's in our set. Here we update that to be 0 to update the correct set identity. And doing that means to find every single element that's in the set that we're unioning together. Using a disjoint set, we have a find that runs an O of 1 time, a really great running time for find. But the actual running time for union means we have to traverse the entire array. It's an O of n running time, which is absolutely terrible. So what we hope to do is we hope to actually build something that's going to be nearly as efficient in find, nearly that constant time running time, but also ensure that we have an efficient running time in the actual union operation. So what we'll be aiming to do in the next lecture is to use the base ideas here and actually build on it to create a more efficient algorithm to build a disjoint set in a runtime much, much smaller than O of n. So I'll see you there. In the past video, we talked about a naive implementation of disjoint sets that allowed us to do a really, really efficient find, but we found that union had to traverse an entire array. There are a lot of elements of this implementation that worked really, really well, but there's going to be some elements that didn't work so well that we need to change. So let's keep the thing that's the very base of it. Let's keep the array as the thing we're going to be looking up. So in this new implementation, we have an array, but in the array, let's not just store the root identity element itself. Let's store some additional information that allows us to create a structure that's going to be way more easy to union together. Let's look at what this is. So what we're going to do is we're going to continue to use the array where the index is the key. The value in the array is going to be -1 when we actually found the representative element. Otherwise, the representative element is going to be the index of the parent itself if we haven't found the representative element. And what this means is we're going to call this an uptree. And this uptree is going to look just like this. Here, when we originally have 4 elements, 0, 1, 2, and 3, which are all in their own sets, the uptree is going to have -1 as all of the values inside the array to note the fact that we've found the identity element. And we can visually represent this uptree as the element 0, 1, 2, and 3 in their own little trees pointing up. But what we can do is we can start unioning these things together to see how this uptree actually works. So suppose I want to union the element 0 and 3 together. So to do that, I'm going to connect 0 to the 3 tree or 3 to the 0 tree. So I'm going to go ahead and keep 0 on top. And then I'm going to move the 3 element to point to 0. So what this means is 0 is the identity element, and 3 points to 0. So we look at index 0 to see what's happening next. 1 and 2 are still in its own trees. So they have the value of -1. Next, we're going to go ahead and union 1 and 2 together. So keeping 0 and 3 unchanged, it's going to be -1 in index 0 and 0 in index 3 to say that 3 needs to look at index 0 to find out what the identity element is. Now 1 being unioned with 2 means that 2 should look at 1 to find out its identity element. And the identity element itself is -1 here in index 1. So the uptree itself looks like a same up tree at index 0. But then here at index 1, it is the identity element, so it just points up. But 2 points to 1 itself. So now it gets really interesting. Now we can actually union together 0 and 1. So these are two elements in two different trees, and we want to union them together faster than we were able to do in the simple implementation we did earlier. We don't want to traverse the entire array. So let's look at this tree and see what we can do. Here we have the tree 0 and 3 and the tree 1 and 2. To update the identity element to 1 and 2 to be 0, we simply need to point every single element in this tree to 0. But because 2 points to 1 and we can follow along, we simply need to point 1 to 0 instead of pointing 1 up. And now we have created a setup where we've updated a single pointer and yet updated the identity element for everything in the tree. So let's see how this array works. So 0 and 3 remains unchanged, negative 1 and 0, as well as the element 2 remains unchanged, so that points to 1. And now element 1 simply points directly to 0. So now both element 1 and element 3 point to 0, so we know that both these elements point to whatever the identity element of the element 0 is. Since the value in element 0 is negative 1, we know 0 is the identity of element itself. So our entire uptree says that 0 is the identity element for everything. 1 points to 0, as well as 3 pointing to 0. And finally, 2 points to 1. So notice that we're building up this tree where we have pointers that are all pointing up to the identity element itself inside of this uptree. And notice how the union operation required us to only update a single pointer. So looking at an entire disjoint set, here is an example that has a whole bunch of stuff inside of several different sets, just like the example we started with when we talking about disjoint sets. And here I made one purposeful mistake so that we can actually identify what it is and go in depth about what it means to build an uptree. Let's take a look. So here we see the uptree has the array implementation down here, and I have the visual implementation of the uptree up here. Looking at this uptree, we see that the root nodes are 5, 7, 4, and 3. So we expect 5, index 5 has negative 1. This works out well. Index 7 also has negative 1, denoting it's a root node. Index 4 has negative 1, denoting it's a root node. And here, index 3, index 3 is pointing to 6. That's not what this error is actually indicating. The identity element of this set is 3, so one of the errors is 3 should be pointing to negative 1. Let's look at 3's child, 6. Index 6, here we say index 6 is the identity element. Instead, the correct implementation of this array is here 3. So we need to look at 3 to find out what the identity element of this tree is, and it is 3. Now when we union two roots together, we can simply update the root node. And by updating the root node, we're able to union two trees together by adding a single pointer. So now let's look at this. Consider that we just update 4 and point it to 7. Now the tree and everything underneath 4 has the identity element of 7. That's awesome. This is an amazing ability to update the union as quickly as possible and only changing one pointer. What we have is an algorithm that allows us to quickly and efficiently update a data structure that maintains disjoint sets. We'll find that the running time of this is strong, but we can do even better. Because what's the very worst case? The worst case might be a tree that looks like a linked list, where we're linking one node at a time all the way up to the root. So we're going to think about how we can improve this and how we can make an ideal tree, the very best case up tree, in the very next video. I'll see you there. So in the previous video, you learned about an uptree, and we talked about how you'd implement the uptree, and we talked about kind of the worst case running time. Let's actually dive a little bit deeper into the analysis and find out some more. So to do that, I provided the code for us to actually look at the find algorithm. Let's look at that. The find algorithm is simply going to say, if the root node of the tree is less than 0, so if it's negative 1, we know we found the identity element. Otherwise, we need to recursively call the find algorithm to look at the element that's denoted inside the array itself. So that means if we have an up tree that has 4 at the root, then 3 underneath that, 2 underneath that, and 1 underneath that, the running time of this algorithm is going to be proportional to the height of our up tree. Because notice if we find a 1, finding 1 means we have to look at 2. And looking at 2 requires us to look at 3. Looking at 3 is going to require us to look at 4. So the deepest node in the tree dominates the amount of time it's going to take us to look at the tree itself. So we're going to say the running time of this up tree is going to be O of h. And in the worst case, h is going to be equal to n. So all of our data may be a single linked list. And if our worst case is O of n, then we've done no better than our naive implementation. What we hope is we hope to build an up tree that allows us to create a tree with an ideal structure. So think about what we'd love for an ideal structure to be. We know that every node may not be an identity node, so we can't have everything with a value of -1. But what we could have is we could have a single identity node as a root node, and every single child could be right underneath that root node. So let's look at what this might look like. So if we have the element 4 as our identity element, our ideal up tree has the element 3, 2, 1, 0, and anything else all pointing to 4 itself. So notice that this tree is extremely flat. There's only a height of 1 in this entire tree. This is fantastic, because that means even if we find any node that's not an identity node, the worst it has to do is look up one node, find that that value of that node is negative, and because that value is negative, we found the identity node. This is absolutely fantastic and ensures that we have a constant running time. So what we want to do is we want to build trees that is as close as possible to that ideal tree so we don't end up in this worst case O of n type situation. So we're going to just study a few different techniques that we can do that when we actually do a union, we can be smart about the union. When we do a find, we can be smart about making sure that every other find after us runs a lot quicker. So we're going to look at how to do a smart union and path compression in the next few videos. I'll see you there. In the previous video, you learned about up trees, and you learned how the up tree running time is good, but has a very bad worst case performance when we have something that looks like a linked list. Let's dive into the actual idea of up trees and see if there's any room for improvement, especially as we're unioning two trees together. Here on this slide, we see that we have a tree that is both short and wide, as well as a tree that's like a linked list that really doesn't make us happy. So we've got a tree that has a nearly ideal structure and a tree that has a really, really worst case structure. So two of these, we want to be smart about how we actually union them together. So remember, the running time actually runs proportional to the height. So we want to keep the height of the tree as small as possible. But we also want to make sure that when we union things together, we're not making the runtime of a lot of different nodes worse. So looking at our array implementation, we know that a whole bunch of nodes are really useful because they tell us what our parent is. But there's two nodes that we have just a kind of sentinel value in them. We have the value -1 in two different positions within this array. And that says we've reached a representative element. Instead of using the value -1, I wonder if we can put something that relates to the structure of the tree inside of that index. And we're going to explore two different ways we can use the structure of the tree to do that. One idea is we may want to store the height of the tree inside of the node itself. So when we reach the identity element, it might be really nice to know how tall is the tree beneath us, so we can always make sure that we're adding the shorter tree to the taller tree, so we never make the taller tree taller. So to do that, instead of representing the root node as -1 always, we can represent the root of our tree as the negative value of the height. But we can't just use the negative height, because consider the element 12. The element 12 has a height right here of 0. So to ensure that the height is always negative, we're not going to just simply use the height. We're going to use the height negative minus 1. So the height tree of 0 is going to have the value of minus 1. The height of tree of 3 is going to have the value of negative 4. So here, updating this array itself, we know that the node 4 right here has a height of 1, 2, 3, the longest path to the root. So this has a value of negative 3 plus 1, or negative 4. Here 7 has a height of 1, 2. So negative 2 plus, minus 1 is negative 3. So 7 has a height of negative 3. Now when we union two things together, by unioning by height, what we're able to do is put the shorter tree onto the taller tree. So what this does is, here 7 becomes part of tree 4, and we know we didn't increase the height of the highest tree at all. In fact, we increased the height of every single element inside of our big tree by 1, because it's now the child of the nodes 4. But what we didn't do was we didn't actually increase the total height of the tree at all. And this is fantastic. This means we're really limiting the height, and we're using some extra information inside of the tree. But the one downside about unioning by height is the height of every single element in this larger tree is being increased by 1. So the other thing we may want to do is consider what results in the least nodes actually increasing in height. So to do that, we can look at a second union operation. This union operation is called union by size. In the union by size operation, instead of storing the height at every single root identity node, what we're going to store the size of elements in that set. So in doing so, we're just going to do the negative of the size, and this works out just fine without having to adapt to it. Because think about the element 12. The element 12 is its own root tree. There's one element in the set, so it's going to have a value of negative 1. Here in this set, there's 4 elements, so the identity element 4 is going to have the value of negative 4. Here in this set, the identity element 7 is going to have 1, 2, 3, 4, 5, 6, 7, 8 elements, so it's going to have the value of negative 8. Now when we union by size, we're going to take the smaller of the two size trees and union it with the larger of the size trees. So what that means is, when I union 4 with 7, what I've done is I've only increased the height of 4 nodes instead of increasing the height of 8 nodes. In unioning by size, we're able to build up this tree to be an absolutely great tree that's always going to ensure that the height of the tree increases with as few nodes as possible every step of the way. The great news is it doesn't actually matter if we union by size or union by height, that both of these algorithms ensure that we have a tree that is log in height, that we have a tree whose structure has all of the characteristics of a binary tree, just like what we studied earlier in the semester. So the height of this tree, using either method, is going to be bound by log n. So log n is great, and it's awesome that we have a tree that's going to be no larger than log n. But what we really want to do is not just have something that looks like a binary tree, but we want to have something that looks better than a binary tree. So the second little hack I'm going to do is not just hacking on the union to make the union smart, but to also make sure that find is an incredibly intelligent algorithm. So let's look at a really tall tree that we're going to use something called path compression on. So here in this tree, what we have is we have a tree that's quite tall that we might do a find operation on 5. Doing a find operation on 5, we know that we're going to have to follow 5 to 4, 4 to 2, 2 to 7, 7 to 9, and finally 9 to 10 to find the identity element. What happens here is we've got this really, really long path that we hope to never have to take again. Because what we ultimately know is 5 is going to have the same return value as 4, which is going to have the same return value as 2, and 7 and 9, is after we do this recursion, as we're rolling down our recursion, what we can do is we can take a look every step of the way and actually find out the tree structure can be updated so that every single one of these nodes point to 10 directly. So 7, going back down, knows the result is 10, it can point directly to 10. 2, knowing the result is 10, can directly point to 10. 4, knowing the result is 10, can point directly to 10. And 5 can also point directly to 10. So notice, after this process, we have updated this tree such that all of the elements that were intermittent along the way now point directly to the root node itself. Notice as I remove the edges that we've updated, notice how so few edges exist. And now, given that each of these sub-elements only had a height of 1, we know that each of these elements are now that much closer to the root. So the idea here is by ensuring that whenever we have a path to the root, we're going to go through and make sure that every element that we took along that path now points directly to the root node itself, to make it closer and closer to this ideal perfect tree where we have a root node and a number of other nodes underneath it. So this is absolutely fantastic and the end goal that we're trying to build as we're building an uptree. So the very end of this series of lectures, I'm going to do a little bit of analysis on exactly what the running time of our uptree is, and how well we implement disjoint sets, and how we can use this to build amazing algorithms when we get to graphs. So I'll see you for analysis in the next video. I'll see you there. One of the most beautiful things about this whole uptree algorithm is the fact that running time becomes fantastic. Remember, as we're unioning two sets together, once we find the root node, we need to update only a single pointer. We can find the root node as quickly as possible because every time we do a find algorithm, we're compressing the path to be smaller and smaller and smaller. And we're nearly getting to that constant time runtime. I really, really wish I can tell you that disjoint sets run in constant time. But that would be a little bit of a lie. Instead, the running time of a disjoint set is one of the best running times we ever see in computer science. The running time of this algorithm is something called the iterated log. Let's see what it means to be an iterated log. The iterated log function is denoted as a log star of n. So this is saying this is an iterated log of n, and the iterated log function says it is 0 if n is less than or equal to 1, and 1 plus the iterated log of the log of the number for every value greater than 1. What this means is an iterated log is how many times you can take the log of a number. So let's do the iterated log of base 2 of 2 to the 65,000th power. So an absolute gigantic number. 2 to the 65,000th power, the log of that is going to be the iterated log of 65,000. The iterated log of 65,000 is going to become the iterated log of 16. The iterated log of 16 is going to be the iterated log of 4. The iterated log of 4 is going to be the iterated log of 2, which is then going to become the iterated log of 1, which is 1 itself. So what this means is we have this fantastic algorithm that only requires us to go 1, 2, 3, 4, 5, 6 times through the iterated log when we have an absolute ginormous number. So the running time, the growth of this algorithm, grows proportional to the number of times you can take the log of a given number. So 2 to the 65,000 is an absolute gigantic number. The iterated log of that is 6. This is so close to constant time. We can't say it's quite O of 1 because it does grow based on the size of the input. But the growth based on the size of the input is extremely small. So small that the input is nearly constant. What we actually are going to say to actually denote the entire running time is we know that some operations take longer than other operations. So what we actually know is we know the total number of operations after a series of m find and union operations is going to be equal to the value of m times the iterated log of n. So m operations take m times iterated log of n time. Because this number is so small, because m operations times iterated log of m is so close to m, we're going to consider that the amortized average running time of our algorithm for all practical purposes is O of 1 amortized time. So when we see any of this used inside of a for loop, even though we know this is not constant time, what we're going to do is we're going to say that we're going to just use a constant time running time as the analysis of this algorithm, because this constant time running time is so close to reality. The iterated log is so small that what we have is an algorithm that runs effectively constant time. We know a few operations are going to take longer, so that's why we're going to say it's amortized constant time. And we know that that's a slight lie. But as we build algorithms that have more and more complex data structure around it, we can just assume that this algorithm is a constant time algorithm. This is going to help us really understand exactly the power of how we can use disjoint sets to build really amazing algorithms in the future. So we'll start using this on graphs, which is one of the last topics we're going to talk about in this class. So I look forward to introducing you to graphs and doing some amazing things with graphs. So I'll see you then. We're right now at a really exciting point in the semester. Up until now, you've learned a ton of different data structures and a number of different algorithms on those data structures to do amazing problems with binary search trees, with AVL trees, with arrays and stacks and queues, and a number of different algorithms. Now we're going to arrive to our ultimate data structure. This single data structure is what we're going to be spending the next 4 weeks talking about. We're going to dive into all the different things we can do with this data structure. But before we dive into it, I want to share with you a few different examples of everything this data structure can do. In this first example, you see a graph here that's one of my favorite graphs in the world. This is a graph of the internet as of 2003. So quite an old graph. And this graph is going to show us all of the different aspects of every single node. Every single computer is a single dot. And these computers are clustered together based on their physical location. So here, these big white clusters are believed to often be universities or large companies. The color of the edges denote the region that the edges are in. Green denotes edges in the Americas. Blue denotes edges in Europe. And red denotes edges in Asia. All of these different edges tells us the connectivity of the graph. And this graph's connectivity is the connectivity of the internet. So now the internet's a little bit larger, and it'd be very hard to visualize the entire internet on such a simple visualization. But back almost 2 decades ago, this visualization was able to capture the full scope of the internet. A second graph visualization is a graph visualization that I created with students a few years ago. This visualization maps out all of the prerequisite courses at the University of Illinois. Let's take a look. This visualization is sometimes called constellation graph. Because this constellation graph, you'll see that a lot of courses depend upon other courses. So you can see in this cutout right here that we have a single course, and the size of the circle is the number of courses that is a prerequisite to it. So you'll see that this spans out from here, having a larger, and smaller set of courses as we make this great graph of constellations. You'll see that at the University of Illinois, our STEM fields that focus on science, technology, engineering, and mathematics are the core cluster right at the center that have a large dependency chain between courses. Out here, we see we have small different constellations that are a sequence of courses that depend upon one another, but don't largely depend on any other subject group. Every single subject's colored in its own color, so you'll see most of these constellations are a single color, being things like Spanish 102 is a prerequisite to Spanish 202, which is a prerequisite to Spanish 302. Then you need intro Spanish before you can take intermediate Spanish, before you can take advanced Spanish. The structure of all of the courses and their prerequisites make this absolutely beautiful constellation. And it's just another application of how we can use nodes and edges between nodes to actually create something that has a lot of meaning. One of the most interesting things with graphs is to be able to solve real problems with graphs that affect our everyday life. So being here at the University of Illinois, one big problem we have is the problem of being able to know when we can schedule final exams so that nobody has a conflict. So this next graph is a conflict-free exam scheduling. Let me show you how it works. Every single node in this graph is a course at the University of Illinois. So here might be the course CS400. Another node right here might be the course Spanish 202. There exists an edge if there is at least one student who's taken both CS400 and Spanish 202. So in this case, because this graph has an edge there, we know there is a student who's taken both. That's awesome. If we look at another course here right now is going to be Agricultural Sciences 418. So an agricultural science course doesn't have an edge between CS 400. What that means is this semester there are no students who are both in Agricultural Science 418 as well as CS 400. Because there's no overlapping students, there's no edge, which means that can have an exam at the exact same time, and no students would be in a conflict. The total result of this graph is if we can label every single node with a different color or a different shape, then we know that the collection of all the different colors and different shapes, such that no two colors or shapes are touching each other, is a collection of times we need to schedule exams. And because no two colors are touching one another, we know that everyone in the university can take an exam without having a conflict with another exam. And you'll see this graph does exactly this, that it creates a conflict-free scheduling such that none of the two nodes in this graph, these two triangles that are turquoise, they have no edge connecting to each other. So all of these turquoise triangles, all throughout the graph, are different courses that can take simultaneous exams, because this is a subset of courses such that no student is in two of those courses. And notice that we labeled this graph with about 12 different shapes. And the 12 different shapes that we labeled represents the 12 different times that we need to give exams, so there's absolutely no conflicts. So this graph is a classical problem known as the graph coloring problem. This is a particularly hard problem and a problem you're going to deal with in a class beyond CS 400. But I wanted to show you exactly all of the problems that you can represent and impose onto a graph before we even get started implementing graph. Because I want to show you why we care about this data structure and why we're going to spend so much time with it this semester. So you're going to be able to dive into graphs and have a deep understanding of it by the end of this course. So let's get started learning about graphs, and I'll see you for the first video coming up next. Before we dive into actually implementing a graph, let's talk about a little bit of vocabulary about graphs so that we can have a common understanding of exactly what we're talking about. Looking at a sample graph, we have a series of graphs here, and I'm going to always refer to the big graph as the capital letter G, and G is a collection of vertices and edges. Here inside the graph G, we have three subgraphs, G1, G2, and G3. These graphs are disconnected because there's no edge that's shared between G1 and G2, but G1 itself is a connected graph because every node inside of G1 can be connected through the various edges. I'll use the term node and vertex interchangeably. When I say node or when I say vertex, you can think of all of the sets of nodes or all the set of vertices. These two terms are completely indistinguishable. If you come from a background of mathematics, you're probably used to the term vertex. If you come from a background of networking, you're probably used to the term node. On the other side, the term edge is universally used. So whenever you hear the term edge, that's always going to mean the connection between two nodes or the connection between two vertices, depending on the choice of words you use. We're going to define the variable in to be equal to the number of vertices in the graph. So if we count the number of vertices, that's going to be defined as in. If we count the number of edges, that's going to be defined as the variable im. So in and im are going to be the two terms that we're going to talk about a lot. A few different things to talk about when it comes to this graph. One term is we have the idea of an incident edge. An edge is incident to the node if it is an edge that is directly connected to that node. So all of the edges on a node are its incident edges. Second thing we're going to talk about is the degree of a node. So the degree of the node is the count of how many incident edges it has. So if you look at how many edges are on this node, if that node, for example, here has 3 incident edges, so we say the degree of this node is 3. The third thing we can talk about is adjacent vertices. Adjacent vertices is every single vertex that's adjacent to a node. So if we travel over all the incident edges and see which nodes are connected to it, those are our adjacent nodes or adjacent vertices. So we have the idea of a single node has a number of incident edges. The number of incident edges it has is the degree of that node. And the nodes on the other side of those edges are the list of adjacent nodes. We can also have terms that you may remember from trees. For example, we can have a path. A path is a sequence of vertices through our tree. The second thing is we can have a cycle. A cycle is a path that starts and ends at the same node. So if we travel through a bunch of nodes, and now we have a path, this path is a circle, so we call this a cycle in the graph. And this semester, we're going to mostly talk about simple graphs. A simple graph is going to be a graph that has no self-loops. So that means there's no edge that links back to itself, because that's going to cause some problems as you're moving throughout the graph. You can simply go to your own location. And there's no multi-edges. That is, there's no set of edges that connect two of the same vertices. That if there's a connection between vertex A and vertex B, there is exactly one edge that goes between those two edges. We've talked about already the term subgraph, where we can have a subset of a graph, and any subgraph is going to contain all of the vertices and all of the edges in that particular subgraph. You see we have 3 subgraphs here, as I mentioned earlier. And finally, we have a number of other terms that we'll introduce you to as we come across them. These are things like a complete subgraph, a connected subgraph, a connected component, a cyclic graph, and then a spanning tree, which we'll dive into all of these terms as we get to them as we explain graphs. So this is just a little bit of vocabulary to ensure that we're on the same page as we talk about the graph algorithms that we're going to be talking about. So to begin kind of this discussion, let's do a little bit of math to find out things that we can know about a graph just from the terms that we've already been introduced to. Part of that is going to be some simple questions on what it means to be a graph. So let's dive into these. So how many edges can exist on a graph that is the minimum number of edges on a not connected graph? So if the graph is not connected, we know that there does not need to exist any edges whatsoever. A not connected graph can be the graph ABC, which are all individual subgraphs with no connections. So the minimum number of edges on a not connected graph is 0. Now consider if this graph was connected. If we connect this graph, then we can see every node must be connected to every other node. So the minimally connected graph is going to be a graph where we have a path from one node to every single other node in the graph, and only one path to get there. Here is a minimally connected graph. You'll notice that we need exactly 1 fewer edges than we need nodes. So the minimum number of edges in a connected graph is going to be the total number of nodes minus 1. The next thing we can talk about is what is the maximum number of edges for this exact same thing. So we're going to assume with most of our graphs that we're always going to have a simple graph. So always having a simple graph means there's no self-edges and that there is no multi-edges. So if we start drawing out graphs, we can see for n equals 1, we have just a single node. For n equals 2, we have 2 nodes. For n equals 3, we have 3 nodes, and it's connected. N equals 4, we have 4 nodes. And we can see that these nodes are all connected. And we can look at how many edges this has. When n equals 1, the number of edges is 0. N equals 2, edges is 1. N equals 3, edges are 3. N equals 4, we have 1, 2, 3, 4, 5, 6 edges. So this looks like a nice repeating sequence. And we can define this to be our nice arithmetic sum of n times n minus 1 over 2, which is equal to the order of n squared total edges. So for every single node, we're going to have edges out to every other node. So it's basically itself times, so n being the nodes itself, it's going to connect to every other node, n minus 1 other nodes. But we know that only half those edges can exist, because you're not going to have an edge from A to B and B to A, so we divide that total by 2. This is exactly what we found. We found n times n minus 1 over 2 is the number of edges in a connected graph. Now if the graph was not a simple graph where we can have multi-edges, we can have an infinite number of edges before we run out of vertices to connect. Because think about a graph with just 2 nodes. If it's not simple, we can have as many multi-edges as we want. So you can imagine there is an infinite number of edges that it can exist in a non-simple graph that's going to contain multi-edges. So because of that, we're going to always constrain ourselves to simple graphs this semester. And in future courses, you can dive into exactly what it means when we start having multi-edges. Finally, the very last thing we can ask about is what is the sum of all the degrees of all of the nodes? So if we think about the degree of a vertex, we know that's how many edges there are. If we sum all of them up, we know that there's going to be every single outbound edge is going to eventually have an inbound edge. So the degree of all of the vertices is going to be equal to 2m, 2 times the number of edges on the graph, because here we're double counting the edges. One's going to be an outbound edge on A, the other one that we're going to count is an inbound edge on B, because the degree of A accounts for the outbound edge and the degree of B counts for the inbound edge, despite the fact that the inbound and outbound edge is exactly the same edge. It is the edge between A and B. In the next lecture, we're going to start implementing the graphs and doing exciting things with C++ with graphs. I'll see you there. As we begin to implement a graph, we first need to talk about the abstract data type of a graph and understand what functionality we need to be building against so we can actually make a useful class. Let's look at this. So inside of our graph, we're going to have a sequence of vectors that we're going to store, a sequence of edges, and some data structure that maintains a relationship between these vertices and these edges. In doing that, we're going to define at least 8 different functions on our graph. The first one is we need to be able to insert a vertex given some key. The second thing is we need to insert an edge between 2 vertices and given some data that we might associate with that edge. We of course need to remove the vertex we inserted earlier, and we need to remove the edge. We also need to be able to ask our graph, what are the incident edges given a vertex? We need to see if 2 vertices are adjacent, so whether or not there's incident edge between these 2 vertices. And then if our graph has directional edges, where A may point to B, but B doesn't point to A, we need to know the origin and the destination of an edge, if the edge is directional. This is the basic ADT that we're going to be looking at as we look at different implementations of a graph. The first implementation we're going to look at is what is referred to as the edge list implementation. This is sort of the naive implementation that allows us to just get a graph going very quickly. And we'll discuss improvements on this implementation after understanding how it works. In the edge list implementation, we are simply going to have a list of vertices and a list of edges maintained in a vector or a hash table-like data structure. So here we have on this simple graph u, v, w, and z. And you can see in our vertex list, we have that edge u, or that vertex u, v, w, and z. And in our edge list, we are simply going to maintain a list of edges and have the vertices that they connect as elements as part of the edge list. So u and v are connected through edge A. Edge B connects v and w. Edge C connects u and w. And edge D connects w and z. Now we understand what it means to be an edge list. Now we can look at operations that we might perform on this edge list. The first thing we might want to look at is how to insert a vertex. To insert a vertex is really quite simple. If I want to add a new vertex called k, that vertex k can simply be added to the end of my array or hash table here. So this is an O of 1 operation, because I simply am adding it to the hash table or adding it to a vector. Because we might need to expand the vector, we can say this is actually O of 1 amortized time. The remove vector operation is going to remove a vector from this list. Again, thinking about this in terms of a hash table, we can make a hash table implementation of this in O of 1 time. Checking if 2 nodes are adjacent gets a little trickier. So if we have vertex 1 and vertex 2, checking if they're adjacent requires us to go through the entire edge list. So we need to look at every single element in our list and say, are these 2 vertices adjacent? And to do that, we say, is w and z adjacent? Well, they're not adjacent on edge A, or edge B, or edge C. Only edge D is it done that way. So here we have an O of M algorithm, because we have to go through and look at every single edge before we can find out whether or not 2 vertices are adjacent. So this is going to run in order of how many edges there are in the graph. Likewise, when we need to calculate the number of incident edges, we also need to go through the entire edge list. So this is also going to be an O of M operation to check whether or not, or to get the collection of all of the edges that are incident to a given vertex, because we don't know where that might exist inside the edge list. So these are the 4 key operations that you're going to see on a graph. And here, the insert and removal runs in constant time, but you actually find things about the property of the graph and how connected they are. It's going to run in orders of the entirety number of edges in the graph. So this could become very, very large and very large graphs and may not be a desirable outcome. In some cases, the edge list is the right implementation to use. And we're going to evaluate this implementation with other implementations as we dive into more implementations of a graph. And we'll do that next. So I'll see you there. In the last video, we talked about an edgeless implementation of a graph. Here, we're going to do an entirely different implementation of a graph using an adjacency matrix. Let's look at how this works. Using the same simple graph we saw in last video, here we're going to maintain the same type of data structure. We're going to maintain a vertex list. And this vertex list is going to maintain all of the vertices inside of our data structure, u, v, w, and z, just the same. We'll maintain this as a hash table to get that O of 1 access time. The other thing we're going to maintain is we're going to still maintain our edge list. But that's not going to be it. In addition to maintaining the edge list, we're also going to be maintaining an adjacency matrix. Let's fill out the adjacency matrix first. The adjacency matrix is going to store a false value if there does not exist an edge between 2 vertices. So between u and u, there does not exist an edge because there are no self-edges. So we know that this is a false value, or 0. Between u and v, we know that that edge does exist, so we can say that's a true value, or 1. Between u and w, we know that edge exists as well. Between u and z, we know that edge does not exist, so it's 0. We can continue this. V and v does not exist an edge. V and w does contain an edge. V and z does not contain an edge. And finally, z and w does contain the edge d. And we can just do the upper triangular part of this matrix because we know that the graph here is undirected, so we could just replicate all of this down to the bottom triangle. But we won't worry about doing that since all we need to do is represent it once here in the upper triangle for a non-directional graph. So while we represented everything with 0s and 1s, I think we can do better than that in our adjacency matrix. So 0 happens to be the exact same value as null, but 1, we can not just say 1, but we could link directly to the actual edge in our edgeless structure. So let's see how this works. For vertex uv, we know u and v is connected by the edge a. So instead of having a 1 here, we're going to have a pointer that points directly to my edge list, which contains u, which is the edge between u and v. Likewise, uw is the edge c that connects u and w. Finally, v and w is the edge b, I'll have a pointer to there, that contains the connections between the vertices v and w. And finally, z, w, is this edge, is going to be edge d, connecting w and z. So here we have an adjacency matrix that doesn't just include whether or not those 2 edges, or that edge is connected to those between those 2 vertices, but we have a data structure that actually links us into the edge list ourselves. So what we can do is we can see that these operations are going to become much, much faster than some of the operations beforehand because we can find out what all the instant edges are far faster than we could have by just going through the entire edge list. Let's talk about those running times. To insert a vertex into this still requires us to insert a vertex into our list. So that's going to be our O of 1 insert. But it also requires us to add another row and column to the matrix. Because of that, we need to know that we need to write out a bunch of data corresponding to the number of vertices in the graph. So now this becomes an O of n algorithm because we have to have a row and a column to correspond the new vertex with every other existing vertex in our table. So now adding a new vertex depends on the total number of vertices that are already in our graph. The same argument in reverse can be made for remove vertex, where we need to remove an element from this graph and shrink the table if necessary. Now checking if two vertices are adjacent, v1 and v2, can simply look up into this table extremely quickly. So if we know we have vertex v and vertex w, to index into this table is an extremely fast operation. In fact, it's just looking at data in an array. So to find out whether or not two nodes are adjacent, we can do that in constant time now by the data structure that we maintain. So our adjacent now runs an O of 1 time. Finally, the very last thing to mention is instant edges is going to be the set of all edges incident to a particular vertex. Here, we can simply look at an entire row and an entire column in our data structure. Let's take a look. Here, the entire row for v with the entire column for v is going to know every presence there, every time there's a true value, we know about an incident vertex. So here, we know that v and u are incident, as well as v and w. So looking at the two true values, we're able to get the number of incident edges. And doing that requires just looking at the set of all of the vertices twice. So again, this is 2 times n checks, which is equal to order n. So what we have with an adjacency matrix implementation is we have an implementation of this matrix such that we're able to optimize whether or not we can check if two vertices are adjacent or not. And we can do that check in O of 1 time. This is an amazing result if the algorithm we care about is going to care about whether or not two nodes are connected. The cost of this is an additional runtime when we insert a vertex and remove a vertex. So we see that we have our first trade-off between the different algorithms that we have. We can see different applications are going to want different implementations of the graph. In the next video, we'll talk about a third and final implementation of a graph that has another set of trade-offs. Then we'll explore an analysis of all 3 of these algorithms at once. So I'll see you then. The third and final implementation of a graph that we're going to talk about is the adjacency list implementation. This combines some of the features of both of our implementations so far into this new structure that's going to have some unique properties. Let's take a look. Here we have the exact same setup. We have a vertex list over here, and this is going to be, again, implemented as a hash table, so we have nice O of 1 access time. And we have our same edge list over here. What we're going to do in an adjacency list is we're going to maintain a linked list of all adjacent edges to a given vertex off of the vertex list. So this means that off of u, I'm going to have a linked list that contains the fact that I have edge A as well as the fact I have edge C that are incident to our vertex u. What this means is that here A, I'm not just going to store A, but I'm going to store a pointer to A itself and a pointer to my edge C itself. Here, instead of storing u and v, u can simply store a pointer back to where its location is. So this is u's location inside of my adjacency list. And this is a pointer to u's location inside of my adjacency list here. So what we have is we have pointers that come off of a linked list inside from our set of vertices that link back to the edge list, and the edge list then links back to the linked list elements inside of my adjacency list. So we have pointers that are going both between my list of nodes as well as my list of edges. And this becomes a huge mess of different pointers. Let's look at another one to kind of see how this starts to build out. Looking at the node w to give myself a little bit of space, we're going to see that w has our first edge is going to be the edge wu. This is edge C. So this will have a pointer to edge C. This w pointer inside edge C is going to point back to the w node. This node itself has a next pointer that's going to point to my next edge, which may be edge B. That connects v and w. So again, pointer to the edgeless node for B,
and our W back to our location in our list W. The very last node is node D. D again points to D, and W points back to this node.
So what we have is we have this totally connected world where we've got all of these pointers interconnecting between the edge list and the actual implementation of our node list. And this is a crazy mess of pointers, complicated to think about and implement. But let's see how great the running times are. If we want to insert a vertex, all we need to add is add the new vertex k here at the bottom, and there's nothing else to do. We don't have to worry about creating an initial linked list, because the initial linked list will just be a null pointer, and we don't have to worry about adding anything to the edge list structure. So to insert a vertex is just going to be our O of 1 amortized time, the same as an edge list. The remove vertex, on the other hand, though, is going to be slightly more complicated. Because imagine removing the vertex W. Removing the vertex W is going to require not just removing the vertex W, but also cleaning up this data structure of all of the edges. So in removing the vertex W, we're going to want to make sure that we move through all the degrees of the vertices and remove all of the associated nodes. This is going to run in terms of the number of degrees of the vertex that we're going to try and remove. This allows us to maintain the data structure, removing every single point of the way. Our adjacent is going to be an operation that we can now find is relatively quick, but not as quick as O of 1. So imagine if we need to find if U and W are adjacent. Here we need to either travel to U's list and see if any of the pointers inside U points to a vertex that has V connected to it, or go through all of the things in W and point to a vertex that has W connected into it. Doing so is going to take us either to the degree of V1 or the degree of V2, since we have to go through every single instant edge in their list. So that the totality of this running time is going to be the minimum of those two nodes, of those two values. So the minimum of those two values is going to tell us the smallest list we have to go through, and we can go through the smallest linked list. So it's not quite O of 1 time. It's not as good as an adjacency matrix, but it is pretty good. And finally, to find out the number of instant edges, we simply need to walk the linked list. So this is going to simply be degree of V. So we've done a lot of analysis, and we've talked about a lot of different algorithms. The big picture out of all of this is going to be a table that compares everything together. So let's look at that. Here is all of the different implementations built in a single table. And let's look at this table. So the amount of space that's required is going to be n plus m for the edge list and the implementation list. In adjacency matrix, we don't need n plus m. We actually need n squared time, where an adjacency list requires n plus m time. So we can see that in an adjacency matrix, we're going to have the most space, because that matrix can become huge. It's going to be squared by the number of nodes in the actual implementation. The insert vertex time, it's going to be constant time in an edge list and adjacency list, as we discussed, which is great. Only an adjacency matrix is going to require linear time. The remove vertex, we can discuss remove vertex as the actual mechanism, just remove the vertex, or removing the vertex and all the edges. To give an apples and apples comparison, I'm going to examine all of these algorithms by removing the vertex and removing all of the associated edges. To remove the vertex and the associated edges requires us to go through the edge list in our edge list implementation. It requires us to go through our entire matrix in our adjacency matrix, but only requires us to go through the linked list in our adjacency list implementation, just requiring a degree of V operations. This is the best algorithm here. To insert an edge requires O of 1 time in every single case. We can simply add it to the edge list, so they're all great implementations. Likewise, removing an edge is also a constant time operation. Finally, the set of instant edges is something we've talked about with all of these algorithms. To find the instant edges in an edge list, we have to go through the entire edge list. To find the instant edges in an adjacency matrix, we have to go through all of the nodes. And to find out the adjacency list in all of the adjacency list implementations, we can just simply do degree of V. So this is going to be the optimal algorithm here. And finally, if we want to find out if two nodes are adjacent to one another, we see that an adjacency matrix has this amazing constant time runtime. while a adjacency list has the minimum of degrees, so it's a worse runtime. The big thing to take away is there's no clear right answer. So I circled and put a check mark by the best category for every single row. In doing so, we see the adjacency matrix is superior if we care about the R-adjacent operation. It's the only one that has the best R-adjacency running time. But on the other hand, if we care about inserting and removing vectors, as well as checking out the list of all of the incident edges, we can see the ideal running time is going to be here for an adjacency list, or in some cases, just as great for an edge list. So there's no single algorithm that works best for all applications. Instead, as we dive into the different applications of graphs, we're going to look at what implementation of a graph is best to use and how and when we should use our different implementations. We'll dive into this next week as we start talking about doing awesome things with graphs. I'll see you then. Now that you have an understanding of how to actually implement a graph inside of C++, let's talk about doing things with that graph. One of the first things we're going to want to do is we're going to want to do a traversal of this graph. And traversals are something we've already talked about. You've traversed trees and talked about many different algorithms for traversing a tree. Now we want to apply the same idea of a traversal to a graph. We're going to see it's somewhat similar, but also very different. Just like a tree, a traversal is going to visit every single node exactly once. But what's different about a traversal is that we absolutely have some problems that we need to deal with when we have a graph as opposed to a tree. Let's look at some of those. So a traversal is going to help us find interesting substructures. Inside of a tree, we know that the tree is ordered. We know that there's a root node, and we can go down from the left and the right child. There's an obvious start to the tree traversal. And then in addition to that, there's a notion of completeness. We know when a tree is finally finished because we can say we have visited every leaf node. We've talked about how you can do an in-order traversal and you know exactly when you're done. A graph has a lot of weird properties that trees don't necessarily have. So here in a graph, we don't know a natural ordering of all these nodes, so they're not ordered. A second thing is there's no obvious start. Where would you start on this graph right here? Would you start at the middle node? Would you start at the top? Would you start at the left? All of these could have valid arguments on where to start. There's no obvious place to start. And there's no notion of completeness built into a graph. That is, a graph's not necessarily going to be entirely complete. That graph is going to be possibly looping around a whole bunch. We're going to have to maintain some sort of data structure to ensure that we're not stepping on a node for a second time. Because remember, traversal needs to visit every single node exactly once. One of the first traversals we want to talk about is the breadth first search traversal. This traversal is going to do the exact same thing as when we did a breadth first search traversal in a tree. Specifically, we're going to visit all of our children nodes before we visit any grandchild. So that means we're going to visit all of our adjacent nodes before we visit any of their adjacent nodes. So to do that, we're going to use the same data structure we used before. We're going to maintain a queue, and this queue is going to help us organize our traversal through a graph. Let's take a look. So here, at vertex A, I'm going to go ahead and start by maintaining a data structure that's going to help us with this traversal. So at A, we have A, B, C, D, E, F, G, and H as all of our different nodes. And A has nodes B, C, and D incident to it. B has nodes A, C, and E. C has nodes A, B, D, E, and F. D has nodes A, C, F, H. E has nodes B, C, and G. F has nodes C, D, G. G has nodes
EFH, and H finally has nodes DG.
This is a list of all of the instant vertices off of every single vertex. This is something that's maintained as part of our graph data structure itself. Now we can think about BFS traversal. I'm going to start with A, but I could start anywhere. I'm going to add A to my queue, and then A is going to also be the first thing that's then removed from my queue. When I remove A from my queue, I can mark it as visited. So A has been visited, and we can queue up all of its instant edges, or instant nodes, B, C, and D. So now, here in my queue, I can go ahead and, now that I visited A, look at my next node in the top of my queue. It's B. Mark B as being visited. And now in queue all of the vertices in B that haven't been already visited. So A, or already added. A's already been visited. B's already been visited. C has already been added. E has not been added, so we now add it to the end of the queue. Again, next visit we notice is C. C we mark it as visited, mark C as visited, go through all of C's instant edges. A and B's already been added. D is added, E is added, F gets added to the queue now as the next node to get visited. We repeat this process. D now gets visited. D gets visited. The new nodes on D is F, and F's already here. H gets added. Then we visit, after visiting D, we visit E. And this process continues as, notice the path that we're making. This is the first node to be visited, then all of our children, then all of their children, and only then are we visiting H, and then the very last node to visit is G, because it's going to be a distance of 3 away from any single root. This process of doing breadth-first search traversal using a queue is a key idea of going through a graph and diving into those structures. So here's a finished version of this. You'll notice that I did a slightly different breadth-first search traversal here based on how I did the ordering of my instant nodes. Here, I ordered the instant edges, adjacent edges, or instant nodes off of A as CBD instead of BCD. Because of that, our structure looks slightly different. The C gets visited first, then B, then D. In both cases, you see that all of our children are visited, all of the instant nodes are visited, before any of their instant nodes, or the grandchildren of my root node, are visited. This property is going to hold for all implementations of a breadth-first search traversal. I've provided you guys the code for this so that you can actually dive in and kind of see this traversal really happen. I want to spend just a second and talk about a few of these elements. The first thing is in a breadth-first search traversal, we have our input graph, and then we're going to go ahead and label these as 2 different types of edges. I'm going to label these as a cross edge and discovery edge, so we can talk about interesting properties of this traversal. So what we're doing here is when we have an edge that's between a node that already exists, or a node that's never been seen before, and a node that already exists. So when A first sees B, C, and D, we're going to say that that edge, when we first see that particular node, is known as discovery edge. That discovers something new. We're going to make that edge bold and darkened in our graph. So we can map all of these discovery edges when we first discover that new node. If we've already discovered that node, because it's been discovered by a previous time, we'll call this a cross edge. And I'll just represent this cross edge with dots. So what we have at the end of a BFS is we have the traversal that visits every single node, and we have this interesting structure of how these nodes were discovered. So as part of this algorithm, I'm not just going to give you a traversal, I'm going to also give you this interesting substructure that we'll talk more about. We have this idea of the labeling of nodes as discovered and cross edges, and we initially mark every node as unexplored and every edge is unexplored. We go through our graph, looking at every single one. We either mark every single one as a discovery edge or a cross edge. You have access to this code through the Git repository associated with this course, so you can dive into that and see how this code actually works. In the next video, we're going to talk about what this substructure that we just created using a BFS traversal does, what it means to have a bunch of discovery edges, and what this substructure of our graph can tell us about the structure of the graph as a whole. So I'll see you then. In the last video, you learned how to implement a BFS algorithm, and you learned what a BFS structure looks like. Here today, we want to do a little bit of analysis on what we did and what things we found out through running this algorithm. So one of the first questions we can ask is whether or not the algorithm that we ran is able to detect different components in our graph. Let's look at the code. Here in the code, we can see that at lines 10 through 12, we actually did something that I didn't really explain earlier, but you can see it's clever. We looked at every single node, and we marked it as unexplored initially. And here, this for loop, we go through every node. If it's still unexplored, we travel through the BFS algorithm. So if we think about a graph that has two components, we can see only when we visit one component do we explore all three of these nodes and mark them all as explored. Then here, when we have those two nodes, those nodes will be unexplored in the other component, because only once we actually visit the nodes in the BFS algorithm do we mark them as explored. So because of that, we can simply cycle through, and when we see another unexplored node, we have a new component. Can we count components? Absolutely. By adding line 13 here, we can count the number of components by simply adding component plus plus for every time we call the BFS algorithm. This is fantastic. So does our implementation handle disjoint graphs? Yes. What code handles this? This is the line 10 through 13. And how do we count components? We add on line 13 a component plus plus counter. Second question is, does our implementation detect a cycle? And if we think about what a tree looks like, a tree is going to be a series of nodes that everything's going to be a discovery edge, because we're always discovering something beneath us, because we're always going down. As soon as we travel to a node on the same level, we know that we could take that cycle and completely follow it again and again and again to have a cycle in our graph. Because of this, we know that the existence of a cross edge means that there's a cycle. So does this algorithm detect cycles? Absolutely yes. How do we update our code? Well, let's see exactly where we look at cross edges. So here we see that in lines 26 to 27, this is when we see that a cross edge is labeled. So if we simply say cycle is equal to true, we're marking the fact that a cycle has been detected in our graph. So by adding a line 28 to denote that a cycle has been found, we're updating our algorithm to not just do a traversal, but also count the number of components and determine whether or not there's a cycle. Therefore, does our implementation detect a cycle? Yes. How do we update the code to detect that cycle? We added the line 28 to mark that a cycle is found on our graph. And what is the running time of this algorithm? Well, to do that, let's go ahead and analyze this algorithm and dive into it. To do this analysis, we're going to look at two different lines of code. We're going to look at line 19 and line 21, because those are the two looping structures, and that's going to determine the number of times our code actually runs. So here the while loop at line 19. The while at line 19 says while the queue is not empty. So thinking about what's going to be in the queue is going to contain every single node in the tree, because when we discover it for the first time, we mark a discovery edge and we add that to our queue. So the entirety of all of the runs of this algorithm is eventually going to run a total of n times for every single vertex in our graph. So the while loop at line 19 runs n times. Let's think about line 21. So line 21 says that for every vertex inside of the list of adjacent vertices. So that means that could be potentially every single other node in our graph if we have a fully connected graph. So here we can potentially be up to n, but we also learned some property about our graph. We learned that in our graph, we know the sum of all of the degrees of all of the vertices for every vertex in our graph. That sum, when we account for all n of them, is going to be equal to 2m. So one way of looking at an algorithm is it's going to be an n times n algorithm. That for every single vertex, we're going to have a series of potentially every other vertex connected to it. Or we can say in totality, in the entire graph, there's exactly 2m of these vertices. So what we can do is we can either do the analysis that says that it's n times n, or n squared running time, or we can say it's n time here And independently, we have to add up all of the possible edges here. So that's 2m. So we can either do n times n to get an n squared running time, or more precisely, we can say it's n plus 2m, which is going to be equal to a running time of O of n plus m. So notice that m could be n squared. So if we have a fully connected graph, the number of edges in our graph is going to be n times n minus 1 over 2. So that's going to be n squared edges in our graph. So m may be n squared. But for a graph that's only partially connected, or a graph that is sparsely connected, we can see m is going to be a number closer to n. So when m is closer to n, this algorithm runs actually proportional to n, because it's simply linear time based on the nodes or the edges. So the most accurate thing we can say is n plus m, knowing that m may be n squared. So the best running time we can say for a BFS traversal is an n plus m running time. The last thing I want to talk about is kind of talk about a few different properties of the tree we actually create when we create this tree of all of the discovery edges. So one thing we can talk about is what is the shortest path from A to H. So looking at this tree, we notice this is a tree structure indeed, that starting with the node we started our BFS traversal on, we can simply follow discovery edges, and those discovery edges are going to lead us down a path that gets to H. Specifically, these discovery edges we usually encode as a predecessor vertex. So if we look at H, H's predecessor is going to be D, D's predecessor is A has itself as the predecessor. So we know the shortest path from D to H is the path among discovery edges, so that's going to be A, D, H. On the other hand, we may need to talk about what the shortest path is from E to H, two different vertices. Unfortunately, BFS only gives us the shortest path from our starting vertex. So we don't know, it is not possible to know the shortest path from E to H with only a BFS algorithm. We always must look at only the starting vertex. If we need to know the shortest path, we need to start our BFS algorithm at E or explore another algorithm to give us the shortest path, which we'll talk about in the future. Third question, how does any cross edge relate to the distance that I have between my starting vertex and my current location? And if we think about this, the cross edge is always going to be an edge that's going to get us somewhere nearby where we've been. So if the edge is going to explore a new structure, it would have been a discovery edge, because the discovery edge is going to be the first time we see this structure. So when we have a cross edge, we know that somebody else has explored it already. So that means either one of our siblings or one of our parents have already seen this edge before. So that means a single cross edge is always going to be nearby our existing edges. In fact, by following a cross edge, we will never get more than one further from our root. We'll never get more than one further from our start. So knowing that we're never going to get one further than our start, we know that cross edges are always going to leave us in the same nearby neighborhood relative to our starting location. So this is a key idea that allows us to know that following a cross edge isn't going to do anything crazy. It's going to get us to a different part of the tree, but it's still going to be about the same depth from my starting point. The very last question is, what's the structure made by this series of discovery edges? I've mentioned before that it's a tree, that we're always seeing the shape going down away from the root. And I'm going to argue that this tree is not just an ordinary tree, that this is a substructure called a spanning tree. And a spanning tree is a structure that spans every single vertex in our graph. So that means from every vertex here, we can travel along our discovery edges to visit any other vertex. This idea is it spans the entire graph in a single tree. We're going to dive into what that means and do some more analysis on traversals and spanning trees in the next few lectures. I'll see you then. In the previous videos, we've talked about a breadth-first search traversal, and now we want to dive in and actually do a different type of traversal, a depth-first search traversal. In a breadth-first traversal, we identified all of our children nodes, or our nearby incident nodes, first, and then we visited their children, or their incident nodes. In a depth-first search traversal, we want to go very, very deep, very quickly. In a BFS, we use a queue structure to maintain our data structure. Here, we're going to maintain our data structure using a stack structure. And to make this really, really easy, we already know we call stack frames when we call C++ code. So we won't even worry about the structure itself. Instead, we're just going to visit every single node as we see them, as we move through our recursion. So this algorithm is going to be really, really quick to understand. So let's go ahead and start with node A and go through this just like we did before.
Starting with node A, I'm going to just start drawing a circle as I want to visit every single node around node A. So I'm going to start here, and as soon as I cross an edge, have I seen this edge before? Have I visited D? No. So this is a discovery edge. And now I've moved from A to D. So now at D, let's do the exact same thing. Let's start at D, let's start drawing my circle, and oh, I found a new edge. It's discovering something new, so let's keep going down. Let's keep doing our depth-first traversal. We move to H, again, starting this circle from about the same spot, and oh, H goes to G. Awesome, we have a newly discovered vertex. Here at G, we're going to do the same thing, and we're going to go ahead and start, and oh, we got to J, do a discovery here on J, and now at J, the exact same thing. We're going to look at J, start looking at all of the edges we might visit, and we find that we have an edge from J to K. We've discovered a new node, and finally at K, we can repeat this process for one last time and see at K, we start here, and here we have an edge that no longer discovers something new. At this edge from K to A, we already know about A. A's been discovered. So we're not going to mark this as a new discovered edge. Instead, we want to mark the K edge as a back edge. It gets us somewhere further back in our process. So just like a cross edge inside of a BFS, a back edge is going to be an edge that's not a discovery edge in a DFS. So I'm going to label it with dots, just as I did with the cross edges. So here, adding dots, we now know that's a back edge. Continuing on K, we find that K to E is a discovery edge. We discovered something new about E. And now at E, let's continue on and say, OK, E, have you found, oh, this is now a back edge because we've already seen the node D. So we don't want to do this as a new discovery edge. We've completely finished in E, visit all the edges. We go back to K, we completely finish. I is completely finished. And now here we're back at G. And in G, we need to continue our circle. We find a new edge here. It's already been labeled. So at G, now we see a new edge C. C is a discovery edge. C has a back edge to D. It's already been discovered, and a discovery edge to B. Finally, F is discovered when we visit G and has a back edge to D.
So notice we did this entire algorithm without ever thinking about a queue or stack data structure. We have an implicit stack going on based on the calling stack in our recursive algorithm. But here we're able to build something up entirely by a really, really simple code. So you know that this has the same roots as a BFS algorithm. You can see we did the same process. We just had different ordering of visiting nodes. Let's see how this code differs. Here's a BFS code. All I need to do is remove everything that has to do with a queue, and I'm going to have a perfectly great call stack. So instead of going through and looking at elements related to a queue, I remove all the queue lines, change the cross edges to discovery edges, and make sure instead of enqueuing, I'm going to call a new version of my depth-first search algorithm with a graph on my new node. By making these changes all over, I can modify this code from a BFS algorithm to a DFS algorithm by simply removing a few lines of code related to the queue, calling DFS instead, and labeling it as a back edge instead. So we now have the code that allows us to do a DFS traversal in the exact same way as a BFS traversal, but we visit our deep nodes extremely early in this process. So in the previous time, we did an analysis of the actual code to understand how it worked. Here, I want to do a different form of analysis to see what the running time of the BFS algorithm and DFS algorithms are. And you'll see that this analysis works for both algorithms, and it's another way to compute the exact same running time. We know the only operations that we're going to perform on a data structure like this is going to be operations that involve labeling our nodes. So every time we do any operation, we're always going to do a labeling. So let's count how many labels that take place when we label all of our vertices and when we query them to find out what the next one is. So when we label a vertex, we know that every single vertex we initially have undiscovered, and then we label it as discovered at some point in time. So we do a total of 2 times n labelings, or O of n labels. We label every edge twice as well. So we do 2 times m labels in the edges, or O of m labels. They're originally a undiscovered edge, and then they're either a discovered edge or a back edge. Now when we query our data structure, we know that we're going around every single node. So we know that we're going through every single vertex exactly once. So we visit every vertex exactly one time. This is O of n. When we look at a single vertex, we're going to visit every single one of those vertices' edges. So we know that potentially a vertex can have every single edge connected to it. But we have a mathematics to say it's actually the degree of v for every single time. So we have degree of v for every single one of our vertices. We know we're going to visit every single one of our vertexes. So we know that this is the sum of all of the degrees of v. The sum of all of degrees of v is equal to 2m, which is equal to O of m. So what we have is O of n plus O of m plus O of m plus O of m. So total running time is O of n plus m. This is the exact same running time as doing a BFS traversal. So we can see by doing 2 different analyses, we have 2 different forms of doing a BFS and DFS traversal. Those 2 different forms of traversal are going to both run in n plus m time. And you'll notice this is the optimal running time for running this, because we have to visit every single node exactly once, and we have to visit every single edge exactly once. So there's no way we can do faster than n plus m time. So both a BFS and DFS traversal are optimal traversals running optimal running times for a graph, and they give us some really interesting bits about the substructure, like this spanning tree we talked about in BFS. Next, we want to dive into actually understanding how we can do even more interesting data structures and figure out how we can find out structures like spanning trees and cycles within our graph. So we'll dive into those things in the next video. We'll talk more about spanning trees then. See you there. In the past couple of weeks, we've introduced the idea of graphs, and we've dove into how we can do a simple traversal on a graph using a BFS or DFS traversal. As part of a BFS traversal, you notice that we created a spanning tree that allows us to span the entire graph. This week, we want to focus on creating a minimum spanning tree. We want to find the tree that can be placed over a graph that connects every single vertex in the graph using the minimal total number of edges, or the minimal weight of all of the edges among the graph. So let's look at what we mean. Here our input's always going to be some undirected graph G with usually edge weights that are unconstrained, but they have to be able to be added together. So normally we'll just use integers, but we can think in certain applications these may be more complex formulas that can simply be added together. So given this graph G with edge weights, we know that we want to create a graph G prime that happens to be a spanning tree of the graph. It needs to be a tree, so it needs to not have a cycle because it needs to visit every node exactly once and not have any of those back edges. And it has a minimal total weight across all of the possible spanning trees. So you can imagine there's a lot of different ways to draw paths that connect every single node. But we want to know, how can we draw a tree that connects every single node in the minimal possible way? And there's going to be multiple different algorithms that we can build to figure out how that we can connect these. 2 of the algorithms we're going to discuss is going to be Kruskall's algorithm and Prim's algorithm. They're both going to take different approaches to building the absolute smallest possible tree given a sequence of edge weights that spans the entire graph. This is going to be a really important application whenever we want to see what is the connectivity of any given system and how can we easily minimally travel between 2 different locations. So next video, we'll start diving into the first of these algorithms, Kruskall's algorithm, and learn about how it forms a minimum spanning tree on any given graph. I'll see you then. Today we're going to dive into one of the two major algorithms to find a minimum spanning tree in the graph. This is Kruskal's algorithm. Kruskal's algorithm is going to require a couple of different data structures that you're already familiar with. So let's set up exactly what we need to have to run Kruskal's algorithm, and let's do an example run through a pretty simple graph so you can see how it forms a minimum spanning tree. I've provided a simple graph with a number of edges that connect the different nodes, and every single edge now has a weight on it. So that's a cost of traveling over that edge. If you imagine if you have a road network, that might be the number of miles in every single connection of roads between two different points. So this entirety of this algorithm is going to depend on knowing the shortest route on the entire map. So we're going to maintain a data structure called a min heap that you learned about earlier in this class. And as part of this min heap algorithm, we're going to have an organized list of all of the shortest edge being on top. So the very shortest edge in this graph is AD, and this has an edge weight of 2. The next shortest graph is EH. EH also has an edge weight of 2. And you can see going further, FG is now the next one, has an edge weight of 4. So we have a list that can be maintained as a minimum heap that is always going to allow us to return the minimum edge in the entire graph. In addition to that, we need to introduce the penultimate algorithm we talked about in this course, the idea of disjoint sets. So in addition to our minimum heap, we're also going to have every single vertex as initially its own disjoint set. Remember that we use an uptree to represent disjoint sets. So here I drew every single vertex as its own uptree that we're going to maintain here inside of Kruskal's algorithm. So to run Kruskal's algorithm, we're starting out with a min heap of all the edges and a disjoint set of all of the elements inside of that set. So how Kruskal's algorithm is going to work is we're going to always remove the minimum element from the heap and then check if that element if the two vertices that are part of that element are already in the same set. If they are, we do nothing. If they're not in the same set, we union those sets together. So because A and D are right now in disjoint sets, A and D are going to become unioned together so that we have both A and D in the same disjoint set. Next, we look at E and H. Are E and H in different sets? They are, so we union E and H together. Next, we look at F and G. Are F and G in different sets? They are, so we union F and G together. A and B. Are A and B in different sets? Yes, so we union A and B together. B and D. Are B and D in different sets? They both have a set identity of A. If we follow the up pointers in the up tree, they both get to A. So they are in the exact same set. Because B and D are in the same set, we do nothing. We do not include this edge as part of our minimum spanning tree. All of the edges up to now that we use to union things together are part of this minimum spanning tree. And then G to E. G to E, G and E are different sets, so we go ahead and union the set that contains G and the set that contains E together. So doing that creates these two sets, so that's part of the minimum spanning tree. G to H are already in the same set. They're both in the set identity with E. We do not add this to the minimum spanning tree. E to C is now union with the set that contains E. So this is part of the minimum spanning tree. And finally, C to H. C to H is the E identity is C, H identity is E, so these are both in the same set, so we don't add them. E to F is already in the same set. F to C, already in the same set. D to E. Finally, A, B, and D, our set of those three vertices, can finally be unioned with the set that contains C, E, F, G, and H. So we simply union A with E. And finally, we have a minimum spanning tree where all of the nodes that we visited now completely connect with one another. And we have a path that goes to every single node because we have a single set in our disjoint set at the very end. We did this through a period of repeated adds or repeated checks from a minimum heap, going down from the least cost edge to the greatest cost edge as we went down this tree. Let's actually draw this minimum spanning tree on the graph to see exactly what it looks like. So I see A to D was added, so I'm going to go ahead and bolden A to D on this graph. I then see E to H was added, so I'm going to bolden E to H. I then see FG was added, F and G,
is bolded. I then see A and B was added, so A and B gets added. Notice I did not add B and D, because had I added B and D, I would have created a cycle and no longer had a tree. G to E was added, so G to E gets added. We see this becomes an even more connected tree. Skip GH, add EC. Adding E to C, we see that this edge was added. And then the next edge to get added is D to E. So at this point, you'll see that there's just 2 connected regions before we add D to E. And we see that there's only one edge that needs to be added to fully connect this tree, to get a spanning tree. That edge we added was D to E. So this D to E edge finally connects our 2 individual parts. And now we have one single spanning tree where from any single node on the spanning tree, we can visit every single other node on this graph. This is an amazing property. And Kruskal's algorithm guarantees that not only is this a spanning tree, but this is one of the smallest possible spanning trees for this entire graph. You cannot create another spanning tree that has a smaller value than this particular spanning tree right here. And this result is a fantastic result that allows us to know that this is going to be a minimal path we can take in our system to move around, as long as we care only about the path that spans every single node. So in the next video, we're going to dive into what's the runtime to actually run this algorithm and see some code to actually implement Kruskal's algorithm. I'll see you then. In the previous video, we talked about how to run Kruskal's algorithm. In this video, I want to look at the code that we actually ran so you can see an implementation of it, and we can discuss the running time of running Kruskal's algorithm. Let's take a look. Looking at this, we have Kruskal's minimum spanning tree algorithm. And this algorithm is going to run using both our minimum heap, or our priority queue here, as well as our disjoint sets. So you're going to see the first few lines of code. What we're going to do is we're going to go ahead and set up our disjoint sets for every single vertex in our graph. And we're going to set up our priority queue. Then we're going to set up our final graph T that we're going to add edges to as we remove them from our minimum heap and see if they're in the same disjoint set. So to do this running time analysis, I'm going to go ahead and focus on 2 regions of the code to see what the total amount of time it takes is. The first region is I want to look at building this data structure as well as removing the minimum element from the data structure. And I want to do this with both looking at using a heap or sorted array for my implementation of my priority queue. Because I could just simply use a heap and remove the minimum element every time, or I can use a sorted array, sort it once, and know I have a total ordering. We'll see the different runtimes and compare and contrast them. Let's take a look. The first thing I'm going to do is building a priority queue. If I want to build a priority queue implement with a heap, we know that from when we discussed earlier that we can build a heap in O of n time. So this is a fantastic result, because if we were to use a sort, and if we wanted to sort all of our data, we would need to use a in log n algorithm. Here, it's not going to be O of n because our heap doesn't include n as our data point. Instead, our heap is a heap of edges. So this is going to be an O of m algorithm here. And to sort an array, it's going to be O of m log m. So we know the amount of time it takes to go ahead and create a sorted array or create a heap. Now we want to see how much time it takes to use these structures. So down here in line 13, we can see that while we go through every single edge in our edge list, we're going to want to remove min from those edges. So each remove min operation is going to take log m time when we're doing a heap. Because we have to do that heap, when we remove min, we have to swap at the last element, heapify down. So as part of doing that, we know we have this log m runtime for every single remove min. On a sorted array, though, we can simply remove m in constant time. So it's just an order 1 operation, and that's really simple. Each of these remove min operations, in totality, though, is going to run while we're still looking for edges to add to our minimum spanning tree. So we potentially need to look at every single edge. So we're going to have to multiply both of these by m to get the total running time. So what we know is that after building a forest of elements inside a disjoint set, we're going to have to build a priority queue
and then loop through removing min a total of m times the cost to remove min. So the total running time for all of these algorithms, for the heap, we know that it was m time to build the heap, but it's going to be m times log m time to go about removing the minimum element a total of m times. On the other hand, a sorted array takes m log m time to sort that array, even though it takes only plus m time to actually travel through every single vertex. So notice that the running time of using different structures, it's either m plus m log n or m log n plus m. The total running time is going to be m log m in both cases. That Kruskal's algorithm is going to take time proportional to the total number of edges times the log of the number of edges. There's one term that we haven't considered that I just want to mention. Here we completely ignored lines 2 through 4. The running time to create a disjoint set of n items is going to be n. So we could say plus n here. But notice that n is always going to be smaller than the number of edges. So we know that this is true because we know that this graph has to be connected. So we know that it needs to be at least n minus 1 edges. So m is going to account for those edges. The total running time of running Kruskal's algorithm using the algorithm we just developed is going to be m times the log of m. So it's going to be entirely proportional on the number of edges in the tree. Kruskal's algorithm is one approach to building a minimum spanning tree. We'll now discuss the next approach, a new algorithm called Prim's algorithm that's going to take a whole new view about building the exact same structure. I'll see you then. When we speak about another minimum spanning tree algorithm, after talking about Kruskal's, almost everyone's going to talk about Prim's algorithm. Both algorithms are going to find a minimum spanning tree, but they do so in an entirely different way. Here in Prim's algorithm, we're going to utilize a fact about a graph, which you can prove, which is that if you have two distinct components in a graph, if you have a component u and a component v, the minimum edge that connects u and v must be part of some minimum spanning tree. What this means is if we have a set of nodes that is labeled and a set of nodes that are not part of our labeled set yet, as long as we keep finding the minimum edge that breaks this partition, we're going to be finding one of the minimum spanning trees that exists in this tree. We can define mathematically, using this diagram, exactly what this means. So here we have two sets, a U set and a V set. Imagine we've started labeling things in the U set. If we find the edge E that splits that partition, we know that this edge E has to be part of a minimum spanning tree, and we can label it as such. Let's take this idea and apply it to a larger tree and actually run Prim's algorithm. Here, I'm going to start with just a single node. It could be any single node, and I'm going to call this node part of my labeled set. Everything outside of that node is going to be part of my unlabeled set. So here, I'm going to just choose this node A, and I'm going to call this side of my line the labeled set. So node A is the labeled set, and now to create a minimum spanning tree, I need to find the minimum edge that crosses over my partition between the labeled set and the unlabeled set. Here, this minimum edge is the edge 2. I go ahead and add this edge to my minimum spanning tree, and I redraw my partition. Now again, I look at all of the edges that cross my partition, and I find the minimum one, that is 5. I add that label, and I redraw my partition. Again, do the exact same process, finding the minimum edge. Here, the minimum edge that crosses the partition is this edge 8. Add this edge, and redraw my partition. Here, the minimum edge that crosses this partition is going to be either of these two edges 9. It's totally up to us which one we choose. I'm going to go ahead and choose this DF edge. Update my partition. Minimum edge that crosses this partition is the FG edge with a weight of 4. Update my partition again. So here we have 13, 13, 11, 10, and 16. 10 is the minimum edge here that crosses the partition. And finally, C is the only thing that's outside of my partition. The minimum edge to add it is 5. So here what we've done is we have created a number of different steps that we start with just a single node, and we look at the partition that separates that node in the labeled set from every other node. We find the minimum edge that bridges that partition, add it to our labeled set, and look at the next partition and find the minimum node that spans that partition. This whole process ends up creating a spanning tree that is a minimum spanning tree on the graph based on the partition property we discussed earlier. Let's look at the code to actually implement this algorithm. So the implementation of this algorithm is going to require a few different data structures, and we'll go through this in the code. The first thing we'll see is the input's going to be a graph, and we're going to input the starting vertex. The output's going to be a spanning tree. What we'll do to actually do this implementation is we're going to label every single vertex with two different values. We're going to label the vertex with initial weight of positive infinity, and everything's going to be labeled positive infinity as its weight. And then we'll also label the predecessor node, or the p-value, for every single vertex. So that tells us how this node was added to the minimum spanning tree and allows us to construct the minimum spanning tree at the end of the algorithm. What we'll do first is then set the initial starting node, the node S, to have the weight of 0. Now we know that the priority queue is going to maintain all of the different weights of all the vertices. So we have a priority queue that's going to maintain every single vertex, and it's going to organize those vertices based on the weight that it takes, that vertex currently has, that vertex currently has. So what that means is we have a priority queue that contains B, C, D, E, F, as well as A. A has a weight of 0, and everything else has a weight of infinity. We're going to remove the minimum element from the priority queue. Here the minimum element is A, our starting point. When we remove A, we add it to our labeled set, and now we update all of the nodes incident to A. So that means we look at B, and we say, is the total cost of this edge A to B going to be a smaller division between our partition than positive infinity? It is, so we update B's weight to 2, which updates our priority queue to contain B's weight to be 2. We also update D's weight to be 17, and we update F's weight to be 16. So now we've added A to our labeled set, and we've looked at how adding that label changes things across my partition. I now can ask my algorithm, using the minimum heap algorithm, what is the smallest element among all of the node weights? And the smallest element among all the nodes' weights is node B. So we go ahead and label node B, and we repeat this process by updating B to D across this partition. Now D has a weight of 5 instead of 17, because 5 is smaller than 17. And now BC has a weight of 15, which is smaller than infinity. We continue this process, again adding the smallest node D. So D now becomes part of our minimum spanning tree. B to D here. We update our partition. We update the weights to get to all of our other nodes. So here DC can be reached in 13 now. DE can be reached in 8, and DF can be reached in 9. We add E being the smallest node that crossed the partition, and now we see that we can update EC to be 12, and we find the smallest node is now DF. We add that here, and finally EC. So what we've done is we have actually found an implementation of an algorithm using data structures you already know that will do this logic of finding the minimum node across the cut of the partition. The last thing we want to know is we want to know what is the running time of this algorithm. How fast does it take to actually find the minimum spanning tree of Prim's algorithm? And we're going to do the same analysis that we did with Kruskal's algorithm. We can dive in and see what is the running time it takes to build it with an adjacency matrix and an adjacency list. And I complete those running times for you by just running through this exact code and seeing what's going on. You can see that if we use a heap plus an adjacency list, we can have this n plus log n runtime plus m plus log n. So we have just a nearly similar runtime as we did with Kruskal's algorithm. In fact, if we consider a sparse graph is going to have m being proportional to n. Then the number of edges and the number of nodes are about the same. And in that case, you can see when the number of edges and the number of nodes are the same, we know that this is going to be m log n plus m log m, which means that the total running time is the exact same thing as Kruskals algorithm, that we have an m log m running time. If we have a really dense graph, we know that m is going to be proportional to the square of the number of nodes, that every single node is going to connect to nearly every other vertex in the graph. In this case, we can see that the m becomes n squared log n, which is going to be greater than m log n. So instead, our running time is going to just be bound by n log n here. So for a very dense graph, Prim's algorithm is able to run things proportional to the number of vertices in the graph, not always necessarily to the number of edges in the graph. Though you always notice that this is going to have a plus component, so you're always going to be bound by the n squared. So you're going to see that just like m log n in Kruskals algorithm, Prim's algorithm is going to have the final running time. The big idea to take away from this is we can find a minimum spanning tree using one of two different algorithms. Using those different algorithms, we're going to exploit data structures that we already know to build that minimum spanning tree. And the time it takes to build that minimum spanning tree is going to always be proportional to the number of edges in the graph times the log of the number of edges in the graph, no matter what algorithm we use. And in a dense graph, you're going to find that that runtime is going to be m log m in both cases. We've learned a lot about minimum spanning trees, and we know a lot about how we can build in a really fascinating data structure that lets us dive into doing absolutely amazing things with graphs. We're going to use our knowledge of minimum spanning tree to now solve a real problem that a lot of us have, which is how do we find the shortest path from point A to point B on a graph from any two random vertices. We'll dive into one of the most famous algorithms in computer science, Dijkstra's algorithm, first thing next week. I'll see you then. One of the most famous algorithms in computer science is Dijkstra's algorithm. This algorithm is very, very similar to an algorithm we covered last week, Prim's algorithm, but is completely different in the sense that instead of finding a minimum spanning tree, Dijkstra's algorithm is going to find us the shortest path on a graph. Let's see how Dijkstra's algorithm works. Looking here at this graph, we have a series of nodes as well as edges that connect it. Notice these edges are directed edges, that they have a source node and a destination. So every edge has an arrow. And in Dijkstra's algorithm, we have the code right here to the right. You'll notice the first few lines of code sets up a for loop that goes through every single vertex on a graph and labels the distance to that vertex as infinity and the previous pointer as null, exactly how Prim's algorithm did it. Then we set our initial vertex to 0. We set up the same priority queue that is defined in terms of the distance to every single vertex. We build a heap so that we can have a priority queue of that. And finally, we set up a graph that is going to be our labeled set of nodes that we have labeled. Finally, we're going to repeat for every single node. And we're going to remove the minimum node, add it to our labeled set. And as we go through all of its neighbors, we're going to be updating the weight, just as we've done with Prim's algorithm. So nothing here is new. The only difference now is as we update the weight, if the weight is lower than what we have currently stored, so if the weight is lower than positive infinity, we're going to update it only if not just the edge weight is lower, but the entire distance from the root node or the starting point to the new point. So what does that mean? Let's go ahead and run the algorithm a little bit. Starting at node A, we know node A's value is 0, and every other node's value is infinity. When we visit A, we're going to add A to our labeled set, so it is now labeled, and we're going to update all of the edges that come out of A. So now B's weight is 10, and F's weight is 7. We've now labeled every single edge, so now we get to remove another element and add it to the labeled set. Here we remove element F. Element F is the minimum weight element along all of the nodes. We remove it, and now we have a labeled set that contains both A and B. Updating all the nodes that are adjacent to F, we see that the weight of E in Prim's algorithm we would update to just 5, because the weight of the edge that leads across the labeled set to the unlabeled set is just 5. In Dijkstra's algorithm, the big difference is we're going to not just update it to be 5, but update the entire cost from A. So that means we're going to add it to the cost that F contains. So F has the cost of 7. 7 plus 5 is 12. So the value of E is 12. Likewise, the weight that we're adding to G
is 5 plus 4, or 11. So now we see we have 3 edges that span the set division, the set partition. We have a weight of 10, a weight of 11, and a weight of 12. The minimum edge that spans the partition now has that weight of 10. And we go ahead and add B to our labeled set. We can update our partition. And now we update the weights. So B to C is 10 plus 7, or 17. And now going from B to D is 10 plus 5, which is 15. So here we have our labeled partition again. And now we find the minimum weight. The minimum weight is G. We add G. We update the edge weights. G to E is 11 plus 2, which is 13. It's not smaller than 12, so we don't update that partition right here. And that's the only edge we need to update. Now the smallest number is 12, so we add E to the list. 12 plus 6 is 18. We don't update the CE edge. And there's no other outbound edges. We update our partition again. And finally, the smallest edge here is now D, so we go ahead and update this partition. And finally, we get to 17. We add 17, and then we add 21.
So what we've done is we've ran the exact same thing as we ran with Prim's algorithm, except for the only difference between Prim's algorithm and Dijkstra's algorithm is that at every single point, instead of just updating the weight of the edge, we actually sum the weight it took us to get to the edge that we're leading from and add it to the weight of that edge. So we're getting the total distance from our source node, from A, all the way down to whatever the node we just discovered is. So if we complete this entire algorithm, you can see we fill this algorithm in with a little bit of code that calculates the sum of the two costs. So you can see here I filled in lines 19, 20, and 21 with this sum, that adding the cost of the path to U to V plus the new path that we just arrived at. If that sum is less than the current node stored, we go ahead and update it. As we run the algorithm, we'll see that we get this graph right here. This graph is going to be a graph that labels the entire shortest path and labels every single shortest path from the distance from our starting node to whatever other node we are on the graph. So if I want to know the distance from A to E, I can simply look at the result of this table, and I know that to get from A to E, I have to go via F. F goes via A. So my path goes EFA, or AFE in the forward form, and the distance is 12. You can see that using this table that we generate through Dijkstra's algorithm, we know the precise path to every single node from A using Dijkstra's algorithm. Because of this, we call Dijkstra's algorithm a single source shortest path, or an SSSP algorithm. Dijkstra's algorithm takes a single source. In this case, our single source was the node A. And from node A, it finds the shortest path to every single other node in our connected graph. This means we know the distance from A to B, A to C, A to D, A to E. Dijkstra's algorithm only finds us a single source shortest path, so we have to give it a source node, and it is always going to start from that source node. It does not know the path from B to D unless we make B the source node. We're going to dive a little bit more into how we can apply Dijkstra's algorithm and the things we can do with it in next lecture. So I'll see you then. You just learned about Dijkstra's algorithm and how it's a very similar algorithm to Prim's algorithm with only a modest change to allow us to find the shortest path. Dijkstra's algorithm is amazing in how it works because it handles a lot of edge cases, though it also fails at a few other edge cases. Let's go ahead and take a look at a few edge cases and see how Dijkstra's algorithm performs by quickly running the algorithm on a few different graphs. Here in this first graph, we have Dijkstra's algorithm handling a single heavyweight path versus multiple lightweight paths. So if I want to go from A to B, I want to know the shortest path to go from A to B. Here you're going to see that there's a path that costs 10 to go directly from A to B, and a path that costs somewhat less than 10 that goes through a number of other destinations. So thinking about how Dijkstra's algorithm performs, we know it's going to label everything initially as infinity, which I won't label, and then start labeling things away from A. So C will have a weight of 1, B will have a weight of 10, so we'll choose C first. Then C will update the weight of D to 2, keep going, 2 is less than 10, E to 3, F to 4, G to 5, H to 6,
And now HB is going to be calculated with a weight of 7. 7 is less than 10, so B's node gets updated to 7, and we choose H to B to get from A to B.
So you'll see right here in this previous example, we actually have an example where Dijkstra's algorithm successfully finds taking lots of short paths, which results in a smaller total distance, will be found using Dijkstra's algorithm, despite the fact there's this direct route from A to B. So Dijkstra's algorithm is able to overcome the fact that there may be multiple different nodes that have to be taken. So the actual number of nodes along the path is larger, but the total distance is what Dijkstra minimizes. And you can see it successfully minimizes it in this example. Let's change this example slightly so that the longer path is optimal and make sure it will choose it even among a lot of shorter paths that get us there.
Here we have a single heavyweight cycle, 5, but that 5 is going to be the desired path to take from A to B instead of this longer path of shorter nodes. Let's see if Dijkstra accounts for this. So again, A is going to update B's weight to 5, C to 1. We continue A to C, C to D, G to E, E to F. And at F, we're going to update the weight of G to be 5. We can go ahead and take that edge, even though there may be a tie-breaking case. So G now gets added. And now we update the weight of H to be 6.
Now Dijkstra's algorithm has to decide, using its priority queue, is 5 less than 6? And because 5 is less than 6, we're going to go ahead and use that, add that edge, A to B, at this point, saying the shortest path from A to B is indeed the direct path A to B.
Now we have A to B right here. This is added. And finally, we finish up with G to H. So here, we find that even under the presence of a long path, Dijkstra still finds the shortest path. In the previous two examples, you saw awesome examples of really the power of Dijkstra's algorithm to always find out the very, very shortest path on any graph. The next thing I want to look at is what happens when you start looking at weights that are negative. So in a lot of applications, we may have edges that will give us back a cost. So it's going to reduce the total running time if we actually take a certain path, and that path's going to be denoted with a negative edge weight. Does Dijkstra's algorithm still perform well there? Let's take a look. So handling negative weight cycles, we have, starting with A, we can look at this classic graph that we've seen before and update B to be 10 and then F to be 7. We choose F as our next node. E becomes 12 and G becomes 11. We go ahead and take B, 17, 15. And then we take G, that becomes 11. Now we can go ahead and take F, that becomes still 12. So we take the EF. Then 12 to negative 6, that's going to become 6. We go ahead and find that 6 is the minimum weight, so we go ahead and take 6. 6 plus 4 is 10. And then we take this and we see, oh,
the shortest path is actually a really interesting path.
So the shortest path here, we can look at the path AF, EC. And the path to do AF, EC is 6.
But I think I just found a shortest path, because what if we took the same path that we found earlier,
AFEC, that was 6, and then took the path HGEC. Because adding the path HGEC, so adding the path we have right here, HEGC, we see that to get back to C is going to have a weight of 4 minus 5, which is negative 1, plus 2, which is 1, negative 6, which is 5. So this longer path is 6 minus 5, or 1.
So what happens here is Dijkstra's algorithm wasn't able to find the shortest path, because the shortest path keeps on growing. In fact, the shortest path to C involves looping around to get back to C an infinite number of times, because every time we loop around, our path gets 5 units shorter. So the first time we get there, it's 6. Next time it's 1. The next time it would be negative 4, then negative 9, then negative 14, then negative 19. This algorithm keeps looping around, or the shortest path keeps looping around, and Dijkstra's algorithm is unable to account for this. And in fact, there's something true in all graphs. Anytime you have a negative weight cycle, there does not exist a shortest path. So we absolutely cannot run any shortest path algorithm with the existence of a negative weight cycle. Dijkstra's algorithm does not work under any graph that has any negative weights. So not even a negative weight cycle, not even a negative weight that's not part of a cycle, because Dijkstra's algorithm assumes that everything going out from the source is monotonically increasing. So one of the biggest weaknesses is that Dijkstra's algorithm fails as soon as you bring in a negative weight edge. There's going to be more advanced algorithms that help us solve problems on graphs that look at negative weight edges, though as soon as we have a negative weight cycle, there will never be a shortest path, because mathematically, that shortest path is infinite. Let's look at one final edge case on Dijkstra's algorithm. Let's look at the case where we have an undirected graph, where edges go both forward and backwards. In this undirected graph, we see that Dijkstra's algorithm has no problem. Starting with A, we simply go A to C. That's going to have an updated weight of 1, 3. We go to D, that's 2. E, that's 3. A to B, that's 3. Then B to H is 4. E to F is 4. And H to G is 5. So having undirected edges doesn't phase Dijkstra's at all. So what we know is Dijkstra's algorithm works really great on any graph, no matter what the structure is, so long as every single edge weight is positive. As soon as we introduce a negative edge weight, we can no longer use Dijkstra's algorithm. But Dijkstra's algorithm is a fantastic algorithm to find the shortest path on all usual graphs where we don't have negative edge weights. In the next lecture, we'll dive in and do a little bit of analysis on how this algorithm works, and I will see you then. Right now, you understand how to use Dijkstra's algorithm and all of the intricacies of how to run Dijkstra's algorithm. The last thing we want to discuss real fast is to just do a quick discussion of the running time of Dijkstra's algorithm. So if we think about the total running time of Dijkstra's algorithm, we know that the running time is going to be very similar to the algorithm that it's based on. In fact, let's do a little bit of analysis and see how this differs from Prim's algorithm. Here we see that just like Prim's algorithm, we're going to construct a graph that's going to have every single vertex that's part of this graph. We're going to build a priority queue of vertices and go through every vertex on the graph, just as we did with Prim's algorithm. At every single vertex, we're going to remove the minimum vertex and then go through all of the edges. And as we find an edge that's smaller, we're going to update the weight of that edge. So here, we see that the updating cost of the edge only happens when we need to decrease. And using a special type of heap called a Fibonacci heap, we're able to optimize the Dijkstra's algorithm running time to an amazing runtime that's going to run the exact same way as the best optimization of Prim's algorithm. So the total running time here is going to be order of m, the number of edges, plus n log n, the total number of nodes in the graph times the log of the number of nodes in this graph. This running time is the absolute best running time that you can get in any shortest path algorithm. So even though it's a little bit more than a traversal, it's a little bit more than an m plus n algorithm, that extra log n to the n allows us to find the shortest path while just traversing over all of the edges and nodes. This is an absolutely fantastic runtime and is a great way to find the shortest path and is the optimal algorithm to do so out of every algorithm that exists. Now that you understand the running time of Dijkstra's algorithm and you have a complete understanding of it, let's look at one of my favorite problems in all of computer science. And you'll see this as a fun way of seeing which algorithm you should apply for a real-life problem. I look forward to showing that to you, and I'll see you there in the next video. One of my absolute favorite puzzles in all of computer science is the landmark path problem. This is a really fun problem because the intuitive answer doesn't always actually solve the problem, and you're going to see a different way of thinking about classic graph problems through solving this problem with me. So in the landmark path problem, we have a series of nodes inside a graph, and we want to find the path between certain nodes. In this graph, every single edge has the exact same weight. They all have a weight of 3. And we need to find out what the shortest path is from different locations. We'll start simple, and then we'll add additional constraints to this graph. So here in my first question, I'm going to look at this graph right here,
I'm going to ask, what is the shortest path from A to G? And finding the shortest path from A to G, I'm going to go ahead and simply say, okay, to get from A to G, it looks like I can simply go down to F and move over to G. And this path takes a total distance of 6, and I can do that by traveling over just 2 edges. This is the absolute shortest path to get from A to G. Second thing is we can ask, what is the running time, the fastest algorithm that we can do to find the shortest path? And because we just studied Dijkstra's algorithm, it would seem that Dijkstra's algorithm might be the shortest path. But notice that all of the edge weights are equal. So because all of the edge weights are equal, that means we just need to know the shortest number of edges that we need to travel. And the shortest number of edges we need to travel, not necessarily the shortest path, in this case, them being the same, is going to be exactly what the minimum spanning tree gives us. So instead of running Dijkstra's algorithm, which takes an extra log n time, n plus n log n, we can just run a minimum spanning tree algorithm, like a breadth first search. And a breadth first search is going to find us the shortest path by finding all of our neighbors, visiting it, using the cross edges, doing the entire breadth first search algorithm. And that's going to discover the shortest path in just the cost of a traversal, in just n plus n time. So let's run breadth first search and let's see that this actually works. So running breadth first search, I start with A. I'm going to visit all of my neighbors first, B, D, F. We're going to have a cross edge here from D to B. Then we're going to have new discovery edges coming out from our children nodes. And we can continue this process of adding more discovery nodes and cross edges. And then we continue with more cross edges and a couple more discovery edges. So here, running BFS, we see that we have a path right here that allows us to find the absolute shortest path. It's part of the minimum spanning tree. It still has a distance of 6. We found the exact same thing, but we found it with a faster algorithm. We found it using a spanning tree instead of the shortest path. So even though Dijkstra's absolutely will find the shortest path, there's sometimes faster ways to solve it depending on the structure of the graph. But this isn't just called the shortest path problem. This is called the landmark path problem. So let's introduce another constraint to this problem. Here, I don't want to just go from A to G. I want to go to A to G via landmark L. So I know I must visit L on my way from A to G. So I want to know the shortest path from A to G that happens to visit L. So here I can do a BFS from A to all of the nodes, like I did earlier. And we can see from a previous graph, A to L makes a path right along the bottom of the graph. So I know the shortest path from A to L is here. And then I can run another shortest path algorithm from L, spanning out from L, building what that tree looks like. And we can see then the shortest path is from L to G. So using 2 applications of a breadth first search, we can see the minimum spanning tree that it creates is going to go ahead and find a fantastic solution to this problem. But I don't think I'm done yet. There's a few more questions we can ask about this graph. In total running time, what is the absolute fastest time that we can find this entire path? And in fact, which vertex should we start at? Do we want to start at A? Because that's a starting point. But if we think about this problem for a little bit, we can find that when we actually start at L, we didn't just get the shortest path from L to our destination. In fact, the shortest path from L, a minimum spanning tree on L, is going to get the minimum path from L to every point on the graph. I'm going to argue, because we have a bidirectional graph where all of the weights of all of the edges are equal, and we're creating spanning trees, we know the path from L to A is also the shortest path from A to L. So as long as we find the L to A shortest path, we know that that can be used for A to L. So by running BFS just once, starting with L, we get a spanning tree that shows us a path, in fact, not just a path, the shortest path from the landmark to A, as well as from the landmark to the finale.
Combining these things, we can do the reverse of the L to A path to get from A to L, and then use the L to the finale path to get us the entire path that visits L first. So the solution to one of my favorite problems is that we don't use Dijkstra's algorithm at all. To find the shortest path along the landmark problem graph, we absolutely must start with the landmark, run BFS exactly one time. It's going to give us the shortest path, and we can solve this in just a single traversal of the entire graph. This is a fantastic running time and a fantastic result, and these are some of the problems that you're going to think about as a computer scientist, that you're going to dive in and see, given a set of constraints, and given the entire wealth of algorithms I know, how do I apply the algorithms I know to solve a really, really interesting problem? This concludes our discussion on Dijkstra's algorithm, and really wraps up everything we're going to cover with graphs. We've had an amazing string of weeks where we've talked about all the different applications of graphs. Now you have an immense amount of knowledge all about how to apply graph algorithms to real-world problems. I look forward to seeing all the work you create using some awesome graph algorithms. So I'll see you and see that work sometime soon.